of tweeters have a very positive stance about this handling, Trump's handling, while say 28% has a positive stance. So that's you know, what you might figure out as being the result of the application of sentiment analysis to these tweets. Okay, so of course, I mean, the idea here is that you want to do something like classification, but which is not just classification. So you need to figure out how many, tweets are very positive, how many are positive, etc. And the red bar shows the estimations that have been performed by the algorithm. Okay, so of course, I mean, when the red bar is identical to the blue bar, that's a perfect estimation. While if the two bars are substantially different, that's inaccurate estimation. So what you can see from this plot is that quantification is inherently about distribution. Okay, and in fact, it is also defined as the task of approximating a true distribution by means of a predicted distribution on the tweets. So examples are, say, estimating the distribution of the tweets about this handling COVID-19 across positive and negative, which would count as binary quantification, or estimate the distribution of complaint messages received by hotels across 5 different classes: cleanliness, rooms, service, location, value for money. This counts as single label multi-class quantification. Multi-class because there's more than 2 classes, 5, and single label because, each message has to do with one, and estimate the distribution of the posts about, say, the Apple Watch 3, across, again, very negative, blah, blah, very positive. So this counts as ordinal quantification because we have 5 classes and there is a total order on them. So there are several variants of quantification. As I said, I mean, the task is akin to classification with one key difference. Classification is interested in assigning labels to individual items, while in quantification, we have a more modest goal, okay? So we are simply interested in the distribution of labels, how many items have a certain label. Why is this studied as a task on its own, as a task different from classification? Because there is a fundamental result in the literature that says that using so-called classify and count, so the idea of classifying all of the data items and counting how many have been assigned a certain label, is something that leads probably to inaccurate estimation, inaccurate quantification. So because of this, different quantification algorithms have been proposed that don't rely on classifying count from many different disciplines, including IR, statistics, machine learning, data mining. So quantification is very important in disciplines, especially in disciplines that focus on aggregate results. There are disciplines such as the social sciences, for instance, which are not interested in the needle in the haystack. They are interested in the haystack itself, in characterizing the haystack. So social sciences, political science, market research, epidemiology are all examples of sciences which are inherently and only interested in aggregate results and not in individual results. And so quantification is especially important in these disciplines. So of course, I mean, quantification requires evaluation measures which are different from those that we use in classification. Classification, we use F1, we use accuracy, but those measures, measure the ability of the system to assign the right label to the right individual. But we are not interested in individuals here. Here, the goal is estimating how well the predicted distribution fits the true distribution. So we need different evaluation measures, and different ones have been proposed in the literature. This is, this is quite obvious because quantification has been tackled in very different disciplines, as I had said before. So the idea is, we want to figure out the different qualities of these evaluation measures, find out which one is the best, especially because this has, lots of different consequences that we know about, especially, the fact that if we use the wrong evaluation measure as a loss in a learning system, that needs to explicitly minimize it, we end up getting a bad quantification system, And in order to evaluate the qualities of these evaluation measures, here we adopt the so-called axiomatic approach to evaluating evaluation measures. The axiomatic approach is based on sort of two tenets. The idea is that we want to propose a set of properties that an evaluation measure for quantification should intuitively satisfy. We make a case for why these properties should be satisfied by the measure, and we check via formal proofs, via theorems, which properties a certain measure either satisfies or doesn't satisfy. So the idea is that the best measure is the one that ideally satisfies all of the properties you have make the case for. And the benefit of this approach is that you basically shift the discussion from the individual measures to their properties, shift the discussion from a complex architecture to its building blocks. So this is sort of advantages, I would say. So here in this work, we actually focus on a specific brand of quantification, which is single label quantification. Single label means, well, you have a certain number of classes, let's say usually more than one, I would say, and higher than two, so C1, Cn, and every individual item needs to have exactly one such label, And we focus on single label quantification for several reasons. Because binary quantification is a special case of it, so we also cover binary quantification. Because multi-label quantification, which is the case in which each item can have several labels at the same time, can also be evaluated by repeatedly using for n times a measure for binary quantification. So I mean, dealing with single label quantification also covers implicitly binary quantification and multi-label quantification. And this doesn't cover ordinal quantification, but this is actually a task which is sort of rarely tackled, and essentially the community has up to now come up with one single measure for it. Okay, so we basically leave this for future work. So the main contribution of this paper is that we have proposed 8 properties, let's say common sense properties that we make a case for, and used these 8 properties to analyze the 9 evaluation measures for single label quantification that have been proposed and used in the literature. So the paper presents actually all 72 proofs that this measure satisfies or doesn't satisfy the property. And basically, this is a sort of a work that is a follow-up from a work I did 5 years ago for classification. So let me go through these properties. Okay, so here is some basic notation. I'll actually represent a true distribution, predicted distribution via P and hat P, with hat indicating prediction or estimation. And PC will actually represent the true prevalence of the class C, while hat P will represent the predicted prevalence of class C. And all evaluation measures will be indicated as D. So first of all, I mean, all of the measures that have been proposed in the literature up to now are measures of error. So because these, we actually propose properties for measures of quantification error. And all of the measures proposed so far belong to a class of mathematical functions which are called divergences. You certainly know Kullback-Leibler divergence as an example, but also absolute error is a famous, example of this class. So because they are divergences, they satisfy two properties that I have laid down. One is called the identity of indiscernibles, which says that basically the function value is 0 only if and only if the predicted distribution is identical to the true distribution. And also non-negativity, the fact that if the two distributions are different, so this implies that the value is higher than 0. So these are two basic properties. Well, these properties are sort of uncontroversial because all of the evaluation measures, quantification for proposed so far, satisfy them. And this is true also of two other properties, strict monotonicity and independence, that I have proposed and that I will not go into exactly because they are uncontroversial, because every measure known satisfies them. We actually, yes, have just 2 minutes. We actually just focus on the other 4 controversial properties. Okay, just I will not go through the definition that you can see up there, but we have a property called max, that in a nutshell says that the image or the range of the function is an interval from 0 beta, which is independently of the problem setting. And the idea is that, in this case, it should be easy to judge what, so if a function, if an evaluation function satisfies this, it's going to be easy to judge what a given value of the D means. Okay, and also it should be meaningful to average the results of a system across different samples, even if they are based on classification schemes that have different cardinalities, different numbers of classes. Okay, and there is a fifth property called impartiality. In a nutshell, it says that if a measure satisfies it, it means that it equally penalizes underestimation and overestimation of class prevalence. And the reason is that, the rationale is that, they should be, underestimation, overestimation should be equally treated, unless there is a specific reason for not doing so. So up to now, I mean, all of these properties should be, I think, satisfied by all measures. The last 2 properties that I want to introduce are mutually exclusive. Okay, so why? Because I think that some applications require one and some applications require the other. Okay, so relativity basically means, if a measure satisfies relativity, it means that it penalizes an estimation error of a certain magnitude more if the 2 class prevalence is lower. Why is this so? Suppose that in an application where you have to estimate prevalences of rare diseases, okay? So you estimate, okay, so it's down with time. So my time is finished. Okay, so I guess I had overestimated. Let me cut this short. Okay, so it's there are the bottom line is that we have these 8 properties that you can look up in the paper. We have 9 measures that we have studied, including, as I said, absolute error, Kullback-Leibler divergence, etc., whose form I will not go into, and we have basically figured out, for each of these properties, which ones are satisfied or not. The basic result is that none of the measures proposed so far is completely satisfactory, because if it was completely satisfactory, you should see yes in all in all cells but one, because rel and abs are not let's say, are mutually exclusive. Okay, so the idea is that there is the paper basically argues that one such property, max, is less perhaps less important than others. So if we relinquish, if we sort of waive the idea that max should be satisfied, we are led with the conclusion that the two more satisfying measures are absolute error and relative absolute error, which are also the more mathematically simple, while the KLD ends up in being the most unsatisfactory. And this sort of calls for the fact that maybe also other fields that make heavy use of KLD should take a look at it. Sorry for going over my time, but I think I'm done.
Thank you. So I think we have time for maybe one question or two questions. I know Nicola has a question that he's messaged to me that he has a question. So would you like to ask a question, please?
Thank you for the talk, Fabrizio. From what you learn, do you think that the measures, apart being more or less sound or more or less satisfactory, do introduce any kind of bias in the evaluation, in the outcomes or decisions we may take on their basis? And is there any hope to find a way to quantify that bias or estimate it?
I'll have to ask you to repeat the question because I haven't really understood what you mean by bias here.
I mean, being more or less satisfactory from the point of view of which properties are compliant with. Basically, they deviate from what would be the ideal way of measuring the task. So how big is this deviation? How much does it impact the conclusions we gather? Can we estimate somehow this deviation?
Yes. Okay. So the essentially, if we use the two measures that I ended up in recommending, basically it turns out that they don't satisfy a certain axiom called max, and which basically say that there is all of these measures range on the same range independently of the sample on which you test, independently of the data set, etc. So in a sense, there is some bias, but it's, I would say, a bit minor because it impacts on the fact that the results, the results obtained on different samples are difficult to compare. Okay, but it doesn't impact the comparability of different systems tested on the same samples. So if you test different systems on the same dataset, samples, etc., you're still safe in a sense. Although, I mean, if the max axiom had been satisfied, it would mean that the values that you obtain in experimentation on a specific sample would be much more immediately, understandable.
Thank you, Fabrizio.
Thank you.
I see that there's one question in the chat that Leif as a party proposed. I don't know, Leif, if you want us to turn on your mic.
His hand. Let me turn on his mic. Leif, you can turn on your mic if you want.
Good morning. So Fabrizio,
yes,
I was just
hi.
wondering, obviously none of the measures fit your axioms. I guess you could think about that as either your axioms are wrong or the measures are wrong. But assuming that they're sensible and correct and intuitive as you claim, then how would you propose to change the existing measures then to fit these axioms? Or what would a new measure look like?
Well, that's that's a holy grail in a sense. It's of course. I mean, the conclusion, the conclusion of this study is that the perfect measure doesn't exist yet. But the entire idea of the, say, axiomatic approach to evaluation measures is the fact that the community can discuss, whether these axioms make sense or not, which ones make sense or not, propose new ones, And so if you read the paper and say, I reject the idea that the max axiom makes sense, that's we're done, And otherwise, if the community in a sense agrees that these axioms do make sense, then, there is a hunt for synthesizing a new measure that tries to satisfy them all.
Yeah, exactly.
I don't know whether
exactly
this...
right. The holy grail is to find the
Yes.
perfect measure or the
Yes.
perfect ruler, right? And so, and one of the aspects you brought up was about that they're all focused around error quantification, right? And
say this
so
again, please.
You mentioned that most of the existing measures are based around error quantification, like mean error and so forth, right? And so obviously from our perspective, we're very much interested in satisfaction. So I'm sort of wondering whether, maybe all the current measures are actually inappropriate because they don't really consider user satisfaction in this case.
Well, no, I mean, you can obviously, I mean, every time you have an error measure, you can take its complement, it becomes an accuracy measure. So this is completely, it's not a relevant aspect to say. So I don't think that by focusing on accuracy and satisfaction instead of error, okay, we will get anywhere,
Okay, cool. Thank you.
Thank you, Leif. And thank you, Fabrizio. Everybody will join me in thanking Fabrizio, however we might do that in Zoom, but that was a great talk. Definitely stuff for us to think about. I'm going to invite our next presenter, Nicola, to get his slides set up. He's going to be presenting work that looks at interval scales and how they might help us better understand IR evaluation measures.
Thank you, Diane. Fabrizio, I guess you have to unshare your screen.
Let me check how I should.
Just so the presenters know, I have a timer on my computer. So
do you?
When your 15 minutes runs out, you'll actually hear a little beeping. I'll let it beep for a couple of minutes so you can hear it, and then I'll turn it off so you can wrap up, okay?
Okay, that's great. Thank you, Diane.
How do I unshare my? Okay.
Perfect. You should see my screen now.
Yes.
Great.
Yep, we do. Great. Thank you.
So, good morning, everybody. I'm Nicola Ferro from University of Padova in Italy, and this is a joint work with my two colleagues, Marco Ferrante and Eleonora Losiuk from the same university. So, what is the problem with interval scales? So, in general, we always say that IR is a discipline deeply rooted in experimentation since its inception. And this basically means that we do like to measure things really a lot. So we have plenty of measures and they have tons of properties and we use them in many different ways. But the problem about, one problem about our measures is what are the assumptions behind them? Because depending on the measurement scale they are built on, some operations may be allowed or not. And we do a lot of operations. We compute mean, variance, correlations, statistical significant tests, and so on. So what about if the measures do not comply with the assumptions we have for these basic operations? And if our measures do not comply with these assumptions, how much the conclusions or the statistical analysis we do are impacted by these departures? And obviously, this brings in a more general question about the validity of our experiments. So we need to be, even if this seems to be tiny details, we need to be really careful. Because if we were in a lab with chemistry things, some boom may happen, and so we wonder what about assumptions. In our case, maybe no explosion happens, but we are at a risk anyway. So what is our plan? Basically, we start from measurement scales. There are different kinds of scales with increasing properties. In particular, ordinal scales allow us just to have order among items in the scale, and interval scales are not only ordered, but they are equispaced. So this means that a difference on the scale has the same meaning all across the scale. And this is the basic property you need to compute mean, standard deviation, etc. in a reliable way. And obviously measure is the most typical, temperature is the most typical example of interval scale. Where does this scale come from? There is a theory which is called representational theory of measurement, which basically says that objects, so system runs in the real world, have their own properties, so they have order, they can be combined, etc. And a measurement, a scale, is just a mapping of the real world object onto a numerical domain with a relationship, typically order and concatenation, which respect what happens in the real world. But in our case, it is difficult to apply this approach, because when we think at runs, it is difficult really to agree on an order. Is it better a run with a highly relevant document at the top than a run with two relevant documents a little bit later on, or vice versa? So what is the natural ordering property of the real world objects before numbers? And if it is hard to determine an order among runs, what about intervals? Because to create an interval, you need an order, and you also need the ability to understand what falls in between any two pairs of runs, if there are other runs. And this is an even harder question. But we can create an interval scale only if we have a proper notion of ordering and interval among objects in the real world. Another problem, this is a little bit more technical. The usual way in which we do scales is comparing, checking if there is a linear transformation, like the transformation between Celsius and Fahrenheit. But this assumes that you have a scale to start from, which is something we miss in IR, because we don't know what or whether of our measures is an interval scale. So we had to find a different way, a constructive approach, where we create orders and intervals among runs in the real world, and we introduce a proper structure which allow us to create an interval scale measure by construction. At this point, we can check whether our IR measures are interval scales or not by looking for a linear transformation to this scale. So the summary of what we did is that what we found is that set-based measures like precision, recall, F measures are interval scales. Rank-based measures are interval scales only under very strict conditions, which are hardly met in practice. So all the measures like AP and DCG, etc., are typically not interval scales. And if you go multi-graded, it will be much more problematic for both set-based and rank-based measures. And we also started some experiments to try to understand what may be the impact of departing from interval scale assumptions. So I will go quickly on theoretical part. Basically, what we did is to create a poset over the set of runs. We can identify a maximal chain in this poset, and this ensures us that there is a unique rank function in the poset, and this rank function can be used to create a natural distance which measures the length of an interval. We can check if this natural distance has the property required to be an interval scale, and if so, we have found our core interval scale. And then we can start looking for transformations between this interval scale and our IR measures. Here, I will go through the simplest cases, which are set-based measures and binary relevance. So you see that we have a very simple order, which is the total mass of relevance. So counting how many relevance documents there are. This is the order we can find between runs in the real world. And this allows us to find a measure which is just a discount. And here you can see an example on the right on how runs are ordered in this case. For using this order, basically we can see that precision, recall, and depth measures are all linear transformations of this order, and so they are all interval scales, and they are expected to order runs in the same way. For rank-based measures, we needed to find a little bit more difficult order, which is basically a relevant document in an higher position weighs more than any number of relevant documents in lower positions. If we use this order, we have a total order among the runs, and we can find the interval scales, rank-based total order you see below. Pay attention that this order may be not so easy to accept by everybody, because, for example, we say that one run with a relevant document in the top position is better than a run with all relevant documents apart the top position. So it may be difficult to agree on this strong order. And so in other papers, we have looked for better alternatives, maybe. With this order, in any case, we can find that rank biased precision is the only interval scale measure we have when P is equal to 0.5. So for just a specific value. When P is less than 0.5, rank biased precision is ordinal but not interval. So it does not more equispace runs, and for P greater than 0.5, it is neither ordinal nor interval, and also average precision is not even ordinal. So this is a very strong finding. Where do we see this? So let's start to do some experiments. Let's take the track 8 track, which has 50 topics with binary relevance judgments, a pool depth of 100 and 130 system runs submitted to it. And basically, we did some experiments. So we computed the Kendall-Stau correlation among the different measures. This is a typical thing we do to compare measure. You average the performance of a system across the 50 topics, and you look at how measures rank systems by their mean performance. And you see that precision is almost one correlation with the order, the interval-based order. Recall is less, precision versus recall is just 0.85, but these are typical numbers we are used to. And also you see that rank bias precision with p.5 is one correlation with the interval-based measure. The ordinal version of rank bias precision is a little bit less correlated. The not ordinal and the not ordinal version of rank bias precision is less correlated, and even less for average precision. So this seems to be reasonable, but we have just said that, for example, precision, recall, and F measures are all interval scales and are one of the transformation of the other. So why? And this means that they must order runs in the same way. So why I do see for them a correlation which is not one? Because if they order runs in the same way, I would expect the correlation one. And this depends on the way I compute the correlation, because the usual way is averaging across topic and then ranking runs. But if I do the correlation, thanks Diane, if I do the correlation topic by topic, so for each topic I look at how measures rank the runs, I see that the correlation is perfectly one, and this indicates that they are a transformation one of the other. So why do we have this departure? This is possibly due to what happens when you average across topics, because precision, the average of precisions behaves exactly in the same way as topic by topic, but recall, for example, is normalized by the recall base. So it may use a slightly different interval scale from topic to topic. And so this is why, for example, the correlation between the recall and set-based total order is one topic by topic, but just 0.85 overall. And this is also why we observe a 0.85 correlation between precision and recall, and not one as we would expect. So this is one open question. The other thing we did is to conduct statistical significant tests. Kruskal-Wallis requires just an ordinal scale, while ANOVA requires an interval scale, and look at how many significantly different pairs we obtain and how this changes. And you see that precision basically matches perfectly what happens with the interval scale. So the same number of pairs for both Kruskal-Wallis and ANOVA, while recall is more or less is a bigger number in both tests, and F measure, which is a combination of the two, basically smooths a little bit the results. Similarly, for rank-based measures, just RBP with 3.5 perfectly matches an interval scales in terms of number of significantly different pairs. The ordinal version of RBP is still okay for a test which assumes Kruskal-Wallis, just an ordinal scale, but starts to behave differently for ANOVA, which assumes an interval scale, and even more for the RBP and AP without neither ordinal nor interval scale properties. So, wrapping up, the question, what we have done. Basically, we have seen that it is possible to develop a theory of IR measures grounded in the representational theory of measurement and sound from a mathematical point of view. We have, using this theory, we have determined the scale properties of various state-of-the-art measures, and we found preliminary experimental results that agree with the expected properties of these measures. However, this also opens a lot of challenges for us, because these experimental findings may ask us to rethink how we use our analytical tools, whether we need to account for violations on the scale properties, since they impact the findings. And this again opens the question of what is the general validity, because if we find more different pairs, it means that we will say more often that two systems are different than not. And then there are technical issues about whether the ordering among runs can be agreed by everybody, or we need to find less strict orders. So this is the end. And any questions?
Thank you, Nicola, for that great presentation. So I see we have a couple of questions actually in the chat, the QA chat. So I don't know if you can open that and see that.
Yeah.
But the first question, I'll just read it aloud for the benefit of everyone, and I'll also let you read that to yourself, Nicola. So it says, when you say runs, do you mean only those that are assessed during an evaluation campaign? And if yes, how would new runs that include non-evaluated documents in their result list be ordered with regard to those?
Okay. Hi, Florina. Yes, by run, I mean a typical run of an evaluation campaign. The ordering does not depend on the fact that a run has participated or not in an evaluation campaign. So the ordering will be the same independently from this. Obviously, if a run has not participated, it may not be part of it will not be part of the pool. And so the question is, how good, how robust are our pools? We have chosen track 8 because it is known to be one of the most robust track from the point of view of pooling and so on. So we think we have not suffered from any bias due to this aspect.
Okay, thanks. Then there's one more question in the QA, and again, I'll read it aloud while you read it to yourself. So thanks for the talk. Would you recommend using statistical tests like median, absolute deviation for ordinal IR metrics, which violate having interval scales? And that's from Roger Benham.
Hi, Roger. Yes, something like that. That was the idea we had when, for example, we used the Kruskal-Wallis, because that was requiring just an ordinal scale. And we see that if we just use an ordinal scale, we don't have a deviation on the number of significant pairs. So the suggestion would really be to pay attention at what are the assumptions behind the test, because usually we are more concerned with we have or do not have a normal distribution of the data, which we don't, how much independence there is between the topics they run and so on, if it is same variance or different variance across the samples, which are obviously very important things to care about, but it turns out that also the scale properties may have an impact on our conclusions.
Okay, thank you. I think we're out of time, so I want everybody to join me in thanking Nicola for his presentation. And I see that Damiano has figured out how to do that in the chat by typing virtual clap, and then Fabrizio also shared some gratitude as well. So feel free to copy Damiano's lead. He's also an author of the next paper, which is going to be presented by Julio Gonzalo, who's part of a team of authors. And Julio is going to be telling us about a comparison of filtering evaluation metrics based on formal constraints. Thank you, Nicola.
Hi. Thank you,
one second,
Diane,
Julio,
for chairing the session at
Julio.
5 a.m. for you. And a big thank you to the conference organizers. I think this online conference is being a perfect example of community resilience in these times. So this is yet another paper in the session on evaluation metrics. I promise that if you stay with me, the outcome of the formal and empirical study is a set of very practical recommendations about how to choose an evaluation metric for the filtering problem. So let me start with a bit of motivation. So the filtering problem, in the filtering problem, you have a stream of incoming items, documents, and there are some items that you want to keep and some items that you want to discard. So it's a binary classification problem with priority. There is one class of interest and one class that we don't want. The problem is very simple to define, but actually it's very tricky to evaluate. Just as an example, there are 3 TREC tasks that deal with filtering problems. It's a TREC filtering, TREC spam, and TREC legal. And they all use different metrics with different foundations and different properties. So it is not easy. Let me start with how much measures disagree and when they disagree. So how much measures disagree? Well, they disagree a lot. You can see in this graph that, for instance, the correlation between the F measure and accuracy is 0.5. Same with accuracy and utilities, the correlation is 0.5. And if you look at the logistic average misclassification and the F measure in the bottom of the graph, the correlation is practically inexistent. So there are actually huge differences in how metrics assess systems for the filtering problem. And here it comes our first finding, which is going to be key for the development of the paper. Let us consider non-informative systems. A non-informative system is a system in which the output is independent of the input. The output does not look at what is coming as input. So that means that the probability of a system saying that something is positive, I'm using here the notation positive and negative for the system outcome and relevant or not relevant for the ground truth, okay? So a non-informative system, the probability of a positive outcome is independent from the probability of relevance. So you have this kind of situation. A baseline system that says that everything is relevant is a non-informative system. A baseline behavior that says that nothing is relevant or just takes a random decision or a weighted random decision, these are all non-informative systems, right? So let's go back to the first graph, but now we remove all systems except the ones that are non-informative. So the dots that you see here are all non-informative systems. And if you remember the first graph, this is like the external part of the cloud for its graph, so that the non-informative systems are the ones for which there is a largest disagreement between metrics. And that's a very interesting finding, because then we can characterize metrics by how they treat non-informative systems. And hopefully this characterization will lead to families that we know how they behave and when we should use them. You may think, why should we bother about non-informative systems? We don't want to evaluate baseline silly systems. We want to evaluate real systems which are informative. But actually, when the data sets are unbalanced, near non-informative behavior is quite frequent. And I'm going to show you an example. So this is the depiction of a system output. Every dot is the output for a given test case. And the diagonals, the red diagonals, are baseline behaviors, which is saying that everything is relevant or saying that everything is not relevant. So these are non-informative behaviors. This is the winner system in one competition. And as you can see, there is some magnetism of this line. So the behavior is close to non-informative in many cases, in the sense that the system is trying to guess what is the majority class, and then it puts all the items in this majority class. And this is for the best system in this competition. But if you look in the middle of the table, you can find examples of systems such as this one, in which this non-informative behavior is even more pronounced. You see that many points here are on the diagonal axis, which are non-informative behavior. So actually, it is interesting to see how metrics evaluate non-informative behavior, because many systems have some default non-informative behavior in many cases. So let me summarize the results of our formal analysis and our empirical analysis. And I will start with the formal analysis. And about formal properties, first we begin with a formal constraint or an axiom that comes from the study from Fabrizio Sebastiani that he mentioned earlier. That is a strict monotonicity. So we want every metric to satisfy these axioms that says that if we take an item from the ground class and we put it in the right class, then the new distribution must have a higher metric value. The metric have to increase because the distribution now is better. We have fixed one of the problems. So this is the constraint that we are going to use, but we also define three properties that are defined looking at what the metrics do with non-informative systems. And the first property, we call absolute weighting, is this. So how these metrics evaluate non-informative systems? Well, there is a parameter inside the metric whose value determines which non-informative outputs are better. This corresponds to metrics that have an absolute gain or loss for each item classification. And so metrics that satisfy this property are metrics such as utility, accuracy, or weighted accuracy. Let me put just an example to make it clear what's going on in here. Utility just puts a weight on each of the components of a confusion matrix. So true positives and true negatives are things that the system gets right, and there is a gain, a particular gain for each of these successes, and then false positives and false negatives are errors, and there is a particular loss for each of these types of errors. All the other metrics, in fact, have a similar behavior, and that makes them part of this family that corresponds to this property. The second property that is mutually exclusive with the first one is when a metric evaluates all non-informative systems with the same quality, right? And you can guess that all metrics based on informativeness satisfy this restriction. For instance, mutual information, logistic average misclassification, etc. All these metrics satisfy this restriction. And the third property, which is also mutually exclusive with the others, is about systems, about metrics that for non-informative systems, they reward a large set of positive outcomes. So the quality of a non-informative system grows with the size of its positive output. In other words, these metrics, this family of metrics, thinks that removing nothing is better than removing randomly. And we call this family class-oriented family because this property is satisfied by metrics that focus on one of the classes in particular. And so you have here precision and recall and the F measure of precision and recall. So how can we use this in practice? So I'm going to show you an example. Think about the following filtering task. You want to filter contents about a company name, for instance, the Apple company in Twitter. So you have a stream of tweets that mention the term Apple, and you want to keep the ones that refer to the company, to the tech company, and you want to discard the ones that refer to other things such as the fruit, etc. So in order to choose a metric, we have to think, how should non-informative systems be evaluated? And to do that, defining the task is not enough. We have to think on what we are going to use, how we're going to use the outcome of the filtering system. And so here are three possible scenarios. In the first scenario, we will use the tweets that refer to the Apple tech company to do some targeted advertising. So how should we evaluate in this case? Well, if you are doing a targeted advertising, there is a cost for each ad that you insert, and there is a possible revenue, an expected revenue for the people that see the click, see the ad, and it's relevant to them. So how we compare non-informative outputs, it depends on the revenue and cost balance for each of the types of hits and mistakes that we make. So in this case, we have to choose a metric which is in the absolute weighting family. In the second scenario, so we have the same output, but now what we want to do is quantifying the popularity of Apple. So we're talking about this quantification problem that Fabrizio introduced in this session earlier. In this case, if we want to know the proportion of tweets that mention the Apple company, any non-informative system which do not care about the input are equally useless. I don't care about the outcome proportion because I cannot trust it. So in this case, in this scenario, I have to go for a metric in the informatives family, which discard every behavior that is non-informative. And finally, think about the third scenario in which we want the outcome of the system to do reputation monitoring. We have to monitor everything that is being said about the Apple company to find potential reputation alerts, so something that can damage the reputation of the company. And we have to be careful and handle this from a PR point of view. In this case, missing content that is relevant can be potentially very harmful if we happen to lose a content that can lead to a reputation problem. So this is more recall-oriented problem. And in this case, we should go for a class-oriented family because class-oriented family of metrics penalize less to the systems that if they don't know what they are doing, they don't remove too much information from the string. Okay, so that's how it would be used in practice. So we do in the paper a formal analysis of a large number of metrics, and this is the outcome. As we knew already, not every metric satisfies monotonicity. These are the ones that fail in our case. And we also see that most metrics, every metric except one, satisfy one of the mutually exclusive formal properties, so they fall into one of the three families that I have just described: utility measures, informativeness measures, and class-oriented measures. And finally, this single metric, reliability and sensitivity pair, which does not satisfy any of the properties, so it does not belong to any of these families. So let me stop for a moment in this metric because we will see in a minute that it has interesting empirical properties. Reliability and sensitivity was introduced at ECIR in 2013, and it's a general metric for many problems because it focuses on pairwise relationships. So basically, reliability and sensitivity think that the ground truth is a bag of relationships, and the system output is also a bag of relationships, and then reliability is the precision of the predicted relationships with respect to the ground truth, and sensitivity is the recall of the predicted relationships with respect to the ground truth. If we apply this to our filtering problem, specifying the advocate relationships, what we get is that reliability turns into the multiplication of the precisions for both classes and sensitivity of the recall for both classes. A final part of our formal study is about smoothing. So we know that there are some metrics that do not satisfy the strict monotonicity constraint, and this normally comes from the fact that they have problems dealing with zeros in the confusion matrix. So a possible solution is doing the Laplace smoothing and simply adding 1 to each component of the confusion matrix. This solves the problem for all metrics, and they all turn to be to satisfy strict monotonicity. However, we have a problem, is that if we apply the Laplace smoothing, non-informative systems are not non-informative any longer. So non-informativeness is not preserved, and therefore the metrics do not fall into their families any longer. So we would like to find an alternative that preserves non-informativeness. And this is our proposal. So this is the Laplace version of the probability of a positive outcome given that the item is relevant. So this is like recall for the positive class. And we propose this alternative formulation. So Laplace assumes a prior, which is equiprobability. That's why it adds 1 to every item in the confusion matrix. We propose to replace that with a prior that is non-informativeness. if we are looking at the probability of positive given relative, instead of putting a fixed number into the true positives, instead of adding a fixed number, 1 in the case of Laplace, we replace that for a number that is weighted by the probability of a positive outcome, which could be the non-informative prior. With the formula that you are seeing in the screen, it can be proved that formal properties are now preserved, so that non-informative systems are still non-informative systems. So that's good. We only have to adjust this weight W, and the way we fix it is to make our correction equal to Laplace if there is equiprobability. So if the probability of a positive outcome is 0.5, then the weight W has to be adjusted to a value of 2. And that's how we obtain our smooth version of recall. And we can do that with all conditional probabilities. And this is an example of how we would get versions for precision and recall on the positive class and for precision and recall of the negative class. And in the paper, it's proved that with this smoothing, now all the metrics satisfy the strict monotonicity, and they still satisfy the property that puts them in a particular family. So that's it for the formal analysis. And I'm going to say just a couple of things about our empirical analysis, which are, I think, very practical. The first one is our study on strictness. So given a set of measures, we say that one of them is stricter if it is a lower bound on the quality assessments of the other measures. In our study,
Julio, I'm going to interrupt you. Sorry, we're at time. And so I'm just going to ask you to go ahead and wrap up, which I think you're doing already. So please continue.
Okay, yeah, I'm getting to the end. So, well, let me just say that the strictness and the robustness of the reliability and sensitivity pair are much higher than all the metrics in the other families. So what's the practical consequence of that? So let me wrap up just with the practical advice that comes out of our formal study. So if you have to choose a filtering metric for your problem, you have to ask yourself how non-informative system behavior should be evaluated. And for that, you have to consider the task and the scenario. In particular, how is the output going to be used? If it's clear, then you have to choose a metric family that complies with your requirement. And keep an eye on the rest, by the way. If it's not clear, if you are not down into that precise specification of the problem, then our suggestion is that you start with the reliability sensitivity pair because it's the strictest and the more robust. The strictest means that if you get a good result with reliability and sensitivity, you guarantee that you have a good result with any of the metrics in the other families. And then, of course, we suggest that you include an additional metric from each family to understand better what is going on. And finally, also consider the non-informative smoothing for the metrics that require so to satisfy the basic constraint. And that would be it. Thanks a lot.
Okay, thank you. That was an amazing presentation, as usual. I think everybody enjoyed seeing your use of technology and also appreciated the excellent content as well. Now, I see we have one question from Andrew McFarland, and I don't know if he wants to ask it or if he wants me to ask it. I think I'll go ahead and ask it in the interest of time. You can probably see it there. It says,
sorry,
what are
Diana,
oh, go ahead.
I can try to, yeah, I'm going to open his mic. Okay.
Yeah.
One second. Andrew.
Can you hear me?
You can talk. Yeah.
Okay. Lovely. Yeah. So let me just get one. So essentially, one of the things I thought about when actually is to do with all of these actually, but particularly for this, I've worked in filtering before, is the issue of replicability and reproducibility, which is becoming quite an issue in science generally, not just in IR. And I was wondering what the implications of your work were for measuring systems, filtering systems in terms of these two concepts. You know, obviously you want your metrics to be reliable, such that you could potentially measure reproducibility and reliability. So I'm just wondering what your thoughts were on that.
Yeah, well, you know, this is a very difficult issue, but I would say that the first step towards reproducibility is understanding what you're doing and choosing a metric that reflects what is your goal. So without that, you won't get reproducibility because you don't understand what's going on. So that's the first step towards this goal. I would say that reproducibility has a lot to do with other aspects of experiment design as well. How do you define for instance, the training and the test set? How much do you allow for overfitting that could cause then not to see the same results elsewhere? So it's a much more complex problem than just focusing on metrics. That, as you have seen in our empirical study, we cover part of the features that help reproducibility and generalizability, such as robustness. So from that point of view, our results show that this reliability sensitivity pair is more robust to changes in the dataset than the others. But at the same time, it doesn't fit into any of the families. So if you are clear that you want to go with one of these families, you can use reliability and sensitivity as a side metric that tells you more things about the data, but maybe not to rank systems.
Thank you.
I see that Fabrizio has also asked a question in chat. Fabrizio, would you like to ask the last question in this talk?
Okay, can you hear me now?
Yes.
Can you hear me?
Yes.
Actually, my question is the following. Okay, you seem to give a sort of a specialized treatment to non-informative classifiers or filters or systems, but sometimes you know, a legitimate classifier behaves like a non-informative classifier. Okay, so sometimes if I have a very rare class, and I have a data set where I legitimately believe that none of my items have the class, I will say no for all of them. Okay, so, and my answer is legitimate. So, I mean, do your properties actually account for this?
Yeah, you have to, there's something that is important, that is that we just define properties, so we do not require metrics to satisfy the properties. The properties just describe how they behave. And in fact, the three properties that we describe are mutually exclusive. You can meet one of them, but not the three of them, not even two of them. So it's just a way of characterizing metrics, because we have observed empirically that how they treat non-informative behaviors is what makes them more different. So that's the sense in which we use these restrictions. But of course, as you say, and in fact, there are certain kinds of problems in which you do not care so much about whether the system is being informative or not, but about the specific penalty that you have to pay if you make a mistake, like in the example that I say about putting advertisements, right? So a non-informative behavior can be okay if it gets most of the items right, if it has a high accuracy, then it's right. I don't care so much that it's non-informative because I'm not paying a high penalty. So the outcome of our work is precisely that you have to find out what you want to do with non-informative behavior. And if it's clear what you have to do with it, then you have a lead to find the best metrics for your case.
Okay, thanks.
Okay, if everybody will join me again in thanking Julio for a great presentation. I see you've got lots of great feedback in the chat window, so make sure you have a look at that. So thank you.
Thank you. Thanks a lot, Diane.
Yes.
Ciao,
so
everyone.
I'm going to invite our next presenter to get ready. This is Felipe Morris, and we're going to switch topics a little bit, and he's going to tell us about the impact of group size on collaborative search effectiveness. So Felipe, please go ahead.
Thanks, Diane. So This paper it was originally published at the Information Retrieval Journal, so I think it's one of these sessions. Today I'm going to talk about my work on group size in cooperative search effectiveness, and this was a work done with my master student Kilian Grasshoff and Claudia Half, my supervisor. So, but at the end, what is collaborative search? So we are using it here and also in this talk, mostly with a single search, which a user has an information need. He goes to the normal web search engine and find what he's looking for. But in a cooperative search is a very it's not that new concept. So Ricardo in 1997 has already explored that, where is cooperative search where a group of people, they want to share the same information need. And here, for example, if they want to have a trip together and they want to search about hotels or place to visit, or even medical search can also happen together. And usually those information needs are exploratory, then they're open-ended and multifaceted. So, but how a cooperative search system looks like. So here I put as example SearchX, which is a cooperative search system that we have developed now for 2 years. And you can see a few things that are different than a normal web search. So we have recent queries, which brings awareness with people that you're searching together. So you can see which queries the other people in your group are querying. And you can also divide the labor of the search. So for example, you can avoid to select the same document or read the same document. So you can also add widgets or algorithm division of labor. And you can also share the knowledge with other people that you're sharing the search session. So here you can share the knowledge by saving the documents, but you also can do it on the algorithmic level. And I'm going to explain more about it later. But there is also a need in cooperative search to scale up. I mean, we have online learning platforms where users, learners, they go to MOOCs like Coursera and edX, and also online workspace that we are used to here in this conference. We use Slack, for example, and Overleaf. All those platforms, they support scaling up their number of people that are using, for example, in a group. And here we're interested to see whether this happens in cooperative search as well. The research in cooperative search goes back to 2007 or even more. But one thing that they have most in common, they don't vary the group size of the search. Sorry for that. So they don't vary the group size of the cooperative search groups, and as you can see, only one of these papers has varied the group size, which is a paper from Yoho in 2009. But the type of study that he performed was a simulation study. So the question still remains: what is the impact of the group size in cooperative search? How can we scale up the features that we see, the query history, and also the shared saved documents? So to take a look on how this is impact, we are interested to do I actually study, not a simulation study here in this paper. We invited participants from crowdsourced platform, and we gave them a pre-task, which you find that is very important because priming can help user understand what is collaborative search and what is not, and if they have any collaborative search episodes in the past. We ask them to go to a reading room where we wait for a few participants to join him in the collaborative search phase. And during the collaborative search phase, we give them 3 topics, and we vary the topics title and description, but we keep the task type. Here is a recall-oriented task, and this took 10 minutes for each topic. We use 3 topics from the robust track for in this experiment, which we found the topics that are more difficult with the systems at track that time submitted with AP less than 0.09. So to take a look on collaborative search and the impact of the group size, we propose here 3 variants. The first variant is a S single, which is basically independent search. We ask only users without any collaboration, so no awareness, no division of labor to perform that task. Next, we get the independent search, but we start adding collaborative search features. So here we add the shared saved documents and the query history, and they could also collapse the saved documents in doing the SERP, so they would avoid to see the same documents that the other user would see. So this provide more awareness of the other users are doing in the search, and they also add interface level division of labor. The next variant is where we add shared relevance feedback, but in the system level. So we add the shared relevance feedback, all the documents that the user are saving during the search, and we change the query of all the users. By doing that, we provide a system level share of knowledge. So for testing these 3 variants, we recruit participants from the Prolific platform, and we want originally groups of 1, 2, 4, and 6, and we aim for 10 groups per size. We use the news articles from the Acquaint collection and the 3 topics that I mentioned. During our study, we found that 305 of the participants they were active. So they all performed queries, they saved documents, and so on. And only 25 were not active as we expected. One thing that we found during this study is that keeping the group size for the 3 topics were very hard. So a group would start with 6, but some of the participants could decide to leave the task during the experiment, and the group would end up with 5 at the end of the last topic. We found that that happened in 30% of the groups. So for our results here, we aggregated the groups 3 and 4 and 5, 6, so we can which was 4 was originally what we were aiming for, but we ended up we have 3, for example. So as metric, we use recall-based metric, but we use a group level. So we get all the saved documents that the entire group has done. And here I'm showing the first variant. And the first variant, to simulate larger group size, we randomly, so for example, for a group of 2, we randomly pick 2 independent searchers, we merge their saved documents, and then we do that along the time. So next here, I show the last 2 variants, and I'm gonna keep with these plots to explain a few things about our results. So the first result that we can see from this plot is that as the large group size, as the group size increase, larger the recall becomes, and this is significant for groups of 3 and 4 and 5, 6 versus groups of 1 and 2. But one thing that we couldn't find yet is a conversion of the recall across group size. So the simulation study that Yo has done in his paper, he found that the group recall would converge and keep stable along the session. But this is can be a little bit more on the nature of our task, because it was a limited time task. So we would expect that as we increase the time during the session, that this recall would converge, of course. One thing that we observed in this study, which is the non-synergy effect. In cooperative search, we aim for the synergy effect, where the pairs of collaborators could be more effective than independent searchers. And here we could not find this significant. So this is a find that we were not expecting this study. But and to try to investigate if the division of labor and awareness on the system side had some effect, that we also performed this experiment. And here you can see, comparing these two interfaces, we don't see a high effect of this happening. Lastly, we want to see if the groups, increasing group size would affect the individual behavior of the collaborative search users. And we found a decreasing trend as we increase the group size. There is a decrease on the number of viewed documents and the number of time the users spend viewing documents. So in the paper, we have found that this happens especially because the users, they spend some time scrolling as well, or interacting with the results that the other people in the group are doing. So they end up spending less time viewing documents than as increased group size, and more or less they become overwhelmed with the other users are doing during the search. So the take-home message here in this paper is that we see that the group size is an underexplored field in cooperative search. And in my research and my PhD, we want to really take a look on this, whether we can have group size, increased group size is actually beneficial for collaborative search. And we also found that most findings in simulation studies did not hold up. So we had the hypothesis from the simulation studies, especially the Yoho paper. And we found in the paper most of these findings, we couldn't reproduce it in a real setup, in a user study, in a crowdsourced study. And we see that the choice of the collaboration as well depends on the topic. The interface-based versus algorithm-based is an important factor in collaborative search. And next, in the future, we also think we're going to aim to broaden our investigation to other type of tasks, and also finding users having different roles and tasks during the collaboration. Here, all the users, they have the same task, but we may find that if your users have different roles, they might be more effective at the end. So that's it. Okay, thanks.
Thank you, Felipe, and thank you for preparing that, which I'm sure was really difficult, taking a full paper in a journal into a presentation, and you did awesome, and you even finished early. So well done, and thank you for putting all your work into that presentation. I do want to just, before opening up for questions, and I see Leif has already posed one there, I do want to put in the chat window a URL where you can find out more information about the IRJ, the Information Retrieval Journal, and ECIR partnership, and how you can potentially have your IRJ paper published or presented at ECIR, and actually vice versa. So some ECIR papers will also be published in IRJ. So I put that in the chat window. Make sure you notice that there's a few percentages in there in that URL. So a few characters didn't translate over correctly, but you should be able to easily find it if you type in ECIR IRJ partnership and using your favorite search engine. So great example. And this is the first year that's going on. And again, Felipe was a model for how that can work really effectively. So I'm going to let Leif ask his question, if he can be unmuted.
Thanks, Diane, and thanks, Felipe. So Yeah, thanks, Diane, for actually mentioning the IRJ partnership. Actually, the first several talks this morning in this session have been published in the IRJ. So the reason why I'm saying this is because I'm one of the editors with Tetsuya Sakai and Ryan White. And as Diane mentioned, this is the first year that we've been trying this out. So do consider submitting to the IRJ, and then that will go through a selection process, and you might get to present your paper at ECIR, maybe in person, maybe virtually, depending on how the situation pans out. So if you have any questions, do feel free to contact us as editors as well. So I'll get on to my question regarding this talk. So I think it's really interesting thinking about how people do collaborative search. And so my question that I've posed to Felipe is, do you think there's some type of group effect happening? So often when we work in groups, we have some type of deferred responsibility. Oh, someone else will do that. And so do you think that's perhaps why people in your study, when they're in larger groups, engage less with the documents themselves? Or is it just simply that they're spending more time communicating with each other? We're getting like the mythical man month kind of effect instead.
Yes, so in this paper in special, we didn't let them communicate. So this was one limitation in this study. So we decided to not let them communicate via chat, for example, which is very common in collaborative search. So yeah, so given that, I would say the communication would not be an issue here. So they was not spending time with communication, but rather going through the others' directions. But maybe as you increase the group size, they also don't see space for themselves to read more documents or spending time reading the documents. So this is maybe a finding. So for example, if they're spending less time reading documents that other users are saving, so they already know that other users have saved that document. So why I need you to actually keep reading that document? So they already trust the other users in the session.
Yeah, so is it trust, or is it that they're just slacking off, right?
Yeah, so one thing that might happen is that the what we call the free riders, right, in the group, where groups of people are not very active. So one thing that we didn't look at this paper is the distribution of how active someone is in a group. So this would be interesting for our next study, especially when we attribute different tasks for each person in a group, right? So each person in the group has a different responsibility.
Yeah, awesome. It'd be good to see how that goes. Good stuff. Thank you.
Thanks.
Okay, I think in the interest of time, we'll stop here and ask the next presenter to get set up. But in the meantime, join me in thanking Felipe again for a great presentation.
Thanks.
The last presenter in this section is going to tell us about evaluating effectiveness of the standard insights extraction pipeline for Bantu languages. So great to focus on a different type of language that many of us are not familiar with. And this presentation is going to be made by Joan Biamagusha. So Joan, if you can get everything set up, and I know we have your slides coming in from a different direction, so I'll let you all get organized. Looks like your slides are up, and if you can turn on your mic and I think share your video, that would be great.
Okay. Can you hear me?
Yes, we can hear you. Okay, great. Thank you so much for this. My name is Joan Biamagusha, and I'll be presenting our paper on evaluating the effectiveness of the standard insights extraction pipeline for Bantu languages, authored by me and my co-author, Matibele Nshabaleng. And we're from IBM Research in Joburg, South Africa. So in the next slide, I just show my overview. I'll give a brief background to the area that we're diving into,
and then talk about give you some details of the grammatical structure of Bantu languages, look at what we mean by insights extraction, present our results, and then show how we revise that pipeline. Okay, so in the background slide there, I just discussed how user-generated content is growing on the internet, especially that comes from social media platforms. And there we have the stats of how internet penetration and Facebook penetration rate is growing in Africa. And obviously we are also putting a lot of content on the internet and in our indigenous languages. And whilst it's true that the indigenous language content is much less than, say, content in English or French, it nonetheless contains a lot of details regarding the local context of the people. So this is very important data for us to be able to mine. And so next, we had two main questions, looking at insights extraction and typically looking at it as an unsupervised machine learning task. How well does the standard pipeline work for Bantu languages? Because again, as an unsupervised machine learning task, we just like to get the data, say like a Twitter data set, and apply it to a series of processes and then see what sort of results we get. And if it doesn't work that well for Bantu languages, how can we change it to make it adaptable? Okay. So next, I will give some background on what Bantu languages are. And in that figure, I just show the spread of Bantu languages on the continent. And you can see it's really a large part of the continent. So many of the countries, more than half of the continent's 54 countries have Bantu language speaking communities. And next, you look at the sort of statistics that we're dealing with here. We are dealing with more than a quarter of the continent's billion population, which are Bantu language speaking communities. So these are definitely people who have something to say, and that we should be able to extract the insights of what they're talking about. And looking at the complexity of these languages, they range from between 300 to 600, depending on different linguists. So having a large number of languages presents another level of difficulty, and especially given that they're very under-resourced. And looking at their complex structure, we have three main concepts: the agglutination, the noun class system, and the complex verbal morphology, which I'll explain next. So one key feature of the Bantu languages is that they have two distinct writing styles. Some languages are conjunctively written, which means you glue together different morphemes showing different grammatical units. And I give an example of Runyankwere, which is a language indigenous to Uganda. And the statement, "I like them," is written as Mbakunda, just one word. And there are those which are disjunctively written. As an example is Sepedi, that is a language indigenous to South Africa, and it's written as Kia Barata, and those are three different words that mean the same thing. So we have to find a way of, if we are dealing with a large number of languages, how do we work with languages that are written differently? The next concept in that slide, I discuss what we mean by agglutination. So there are different grammatical units. We are talking about subject, object, verb, tense, aspect, negation. And with agglutination, you typically find one or more of these glued to each other. And so there's an example there of Tibakumureba, meaning they do not see him. And you can see how it is all written as one word, and yet it's actually a sentence. So that's yet another level of difficulty.
Joan, are you still there? I think I've at least lost you.
Okay, so the next difficult concept is the noun classification system, and this is a very important concept in Bantu languages.
Joan, I'm not able to hear you anymore. And I also see one of our participants or attendees also is not able to get a consistent audio feed. So I'm not sure if there's some adjustment you can make on your end. We're currently viewing your slide about noun classification. It might be helpful to turn off your mic and then turn it back on if you're able to hear me. If you're still connected to us and you want to indicate that in the chat, that would be great. We can try to keep figuring out if there's a way to improve the connection.
It seems that she's left, and now it's
She has her hand up, I see.
yeah, I'll promote her to panelist.
Great.
So she can continue. Okay.
Joan, are you back with us?
It takes some seconds, but
Oh, can you hear me?
Yes, you're
yeah.
back. Great.
I'm sorry, I don't know what happened there.
Hey, that's okay. So we were just looking, I can see your other connection is still open. Now it's closed. Great. And we were just on your slide. So I don't think we heard anything about the noun classification slide that's currently displayed. So if you want to just start from there and can carry on, that'd be great.
Okay, thank you. Yes, so noun classification, this is one of the most important features of the Bantu languages grammatical structure. First and foremost, every noun in a Bantu language belongs to a specific class, and the number of classes can range from as few as 7 to as many as 23. So for example, Runyankore, the language indigenous to Uganda, has 20 noun classes. A noun has a prefix and a stem, and the prefix determines the class to which that noun belongs. So for example, the noun person in Runyankore, which is Omuntu, has Omu, the prefix, and Ntu as the stem. And noun classes also determine grammatical agreement for verbs, subject, object, possessives, adjectives, and other parts of speech. And so in the next slide there, I just show just a bit of the noun class system of Runyankore. And as you can see, we have the classes from 1 to 7. The grammatical form is also determined by the noun class, whether a noun is singular or plural. If you're going to have a subject, it's also determined by the noun class. So for example, Runyankore that has 20 noun classes means that there are 20 ways in which you can say something is going, whether it's a boy or a car or something. Depending on the noun class, then you conjugate that verb differently. Okay, so next I discussed the verbal morphology. So the verbal morphology, as we saw with agglutination, where we glue different morphemes to form a single word, is already complex that way. We have multiple tenses. So for example, Runyankore has 14 tenses. And additionally, we have morphemes that are to the left of the verb root. Those typically have subject, object, negation, and tense. And then those to the right of the verb root, which have aspect, mood, and other valency categories. Okay. So just looking at that complex structure, we then discuss insights extraction. And so when we're looking at insights extraction, we considered 7 main processes: text preprocessing, dimensionality reduction, visualization, clustering, topic modeling, sentiment analysis, and network graphing. And we're all pretty familiar with what these entail. And so the main point of our investigation was to see if we have a data set and we apply it to these processes according to that pipeline, can we extract actually valuable insights? And if not, what are the limitations? And next, we look at the materials that we used. We used Twitter data, and again, widely used in Africa, and people tweet a lot in their indigenous languages. We used 20,000 tweets and had two data sets. We had our benchmark data set, which is in English, and then we had a second data set, which was mixed with several Bantu languages, mixed code, and some English. And we left it mixed like this because this is the actual reality of how people tweet. So it really wouldn't be representative for us to try and split it into some like one pure language. And the 6 languages we considered, we had 3 disjunctive languages, and that is Sepedi, Sesotho, and Setswana. And we had 3 conjunctive languages, which is Runyankore, Luganda, and isiZulu. And the methods that we used, so for text preprocessing, we use standard methods. You remove stop words, you expand abbreviations, remove alphanumeric characters, and so on. The only step we didn't perform here was stemming or lemmatizing, and that's because not Bantu languages are generally under-resourced, and not all the languages we're considering had resources for stemming. And so to keep it on an even playing field, we also didn't stem or lematize the English data set. And then we used those other methods for the clustering and the topic modeling and so on. Okay, so in terms of the results, what we found, there were 3 main outcomes regarding the 7 processes. We found that 3 processes needed modification, either modification to add to the process or do things a little differently. And that was for text preprocessing, sentiment analysis, and topic modeling. 3 of the processes, much as they're independent of the actual language, they're still affected by the TF-IDF matrix that we end up with after the text preprocessing. So that's the data visualization, the dimensionality reduction, and the clustering. And then, network graphing, that was really not affected because it's language independent. And so I'll just delve into a few 2 details of these 3 processes that required modification and what sort of modification we found they would need if they were to work with Bantu languages. So looking at text preprocessing.
Joan, you have about 2 minutes left. I didn't stop the clock when we had the technical problem.
Oh, okay,
but
sorry.
Just so you know where we are with time.
Okay, so the main things to note about text preprocessing is that we need to first and foremost distinguish between conjunctive and disjunctively written languages. And then we need to note the difference between nouns and other parts of speech. And in the next slide there, I show a table which shows why we need to to differentiate between different parts of speech. So nouns should not be stemmed. And in that table, I show examples of why nouns should not be stemmed. When you stem the noun and you remove the prefix, you lose the sentiment of the word. And just to give an example of the Sepedi example, where we have in bold, the nouns are bolded in the table there, we have Sepedi and Mopedi. If you stem it, you remove the prefix and just remain with the stem in bold, which is pedi. And pedi doesn't mean anything. So pedi means a language, mopedi means a person. If you stem it, you lose the semantics of the noun. Then in the next table, I just show the different verbal forms that can exist just by verbal extensions to explain why we must stem verbs in order to not have very sparse matrices. And the next table explains the same for adjectives as well. Very many forms for the adjective that have a basic root, and we need to stem to avoid very sparse matrices. The main point for topic modeling is that we cannot use the standard threshold counts, whether it's for tweet length or token count, because as we have seen, due to agglutination, you can have an entire sentence reading represented as a single word. So we had to use all the data sets, all tokens and all tweets for that. And then the most important thing for sentiment is the negation morpheme being agglutinated to the verb, and that is in the next slide there. where negation has multiple forms. Runyan-Kure has both primary and secondary negation that are found at different positions in the verbal form. And so that makes it difficult. If you perform stemming further up in the pipeline, by the time you get to sentiment analysis, you'll find you've lost the negation morphemes, and that will affect the sentiment analysis. And in the final slide there, we show the final architecture that we came up with, a revised pipeline for Bantu languages, where you look at text reprocessing has a lot more going on than you would for a standard data set. So you'd have to first differentiate between conjunctive and disjunctive, and then go further to look at the sentiment analysis, and then perform the part of speech tagging and morphological analysis, and then do the stemming lemmatization, and then the other processes can happen. So the main point is, for this revised pipeline, the sentiment analysis is further up in the pipeline than before, and the text preprocessing has a lot more going on in there. Thank you very much.
Thank you, Joan. If everybody will join me in thanking Joan. That was great. I learned a lot, and it seems like it's very pioneering work in terms of all these interesting and different problems that are related to the language. So I think it's very provocative. We're over time, but that's okay. I would like to take one question from the audience. So would anybody like to ask a question? No questions. Okay, well, if you'll join me again in thanking Joan, and I'm sure she was happy to take your questions offline. If you want to check out her email address on her paper.
Thank you so much.
Email her. Thank you, Joan. And if everybody will join me again in thanking all of the speakers in this session. It's been a great session. I know I've learned a lot. And the next sessions are starting actually pretty shortly, less than 10 minutes, unless they're delayed a little bit starting. And so hopefully we'll all either come back to this room or go into the other room to get more great presentations. So thanks everybody for your time this morning.
Thanks, Diana. Thank all the speakers. Let's say then we have a few time for a coffee break, and remember that we do have the Slack channel, and here you can talk with our sponsors one-to-one. So thank you, everyone. As life asks, where is the coffee break? When you can go to your kitchen, take a coffee.
Hey, it would be good. I don't know if it's possible to mark the papers that are from IRJ on the website, on the ECIR program. I mean, not now, it's obviously not critical or important, but if people go back and look, they can see that those were IRJ papers. I didn't realize they were.
I'll take a note and I'll ask the organizers for that. Okay, here we have.
But small stuff, great session.
Yeah.
Do I need to do anything else, or am I?
No. No, I'll now send everyone to attend this, and I'll start promoting the speakers for the next session.
Yeah, I see Jimmy has his hand raised.
Yeah, please, the speakers, raise your hands. And
I'll see you all later.
Yeah, thank you very much. Okay. 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 I'll be promoting you. Okay, I'll first. Hi, Pavel, can you hear me?
Hi. Yeah.
Okay, you are the chair of the session, right?
Yes.
Okay.
Can you see me?
I'll be promoting the people here. We have Jimmy, Mike, Max.
Hello, I'm here.
Hi. Chris. Fabian. And Alexandros. Okay.
So everyone is here?
Dominic also.
Hello.
Hi. Okay. We have 9 panelists now. We have 8 papers. I think we're missing one.
Hello.
Everyone. Let me check one thing.
Maybe we should go one by one. So
Yeah, I'm first. Can I try taking control of the screen and sharing mine?
Sure. I'll give you a short test. Okay, go ahead. Okay.
Am I live? So do I need to go into presentation mode now?
Yeah. Please. Okay.
Does this
Perfect.
work?
Yep.
Okay.
Good.
All right, so we just do this, and then what are we doing for time cues, warnings, things like that, answering questions?
Okay,
yeah.
So I'll have a timer running, and if time starts to run out, I'll open my microphone and warn you. Okay. So it's 10 minutes presentation plus 2 minutes questions, if I'm not mistaken.
Yeah, I think so.
Wait, is it 10 minutes and the 10 plus 2, or is it 8 plus 2?
10 plus 2. We can do 10.
Oh, okay, that's fine. I misunderstood the email that sent around. I thought it was 8 plus 2 equals 10, but that's fine. We'll have more time for questions then.
Okay. So maybe we should try. So are we? I don't.
If you could,
Are we starting, or we should probably test the other people?
Yeah, we should test the other people, and I think that there's someone that raised their hands that must be the missing speaker.
Oh, actually, no. I'm giving 2 talks. So.
Oh, okay. Okay, then there's no missing speaker.
Yeah.
Okay, perfect.
I'm coming back. I'm giving the other one. I forgot what the other one is, but no, I didn't really forget what the other one is. But
okay, then.
So I think the next one will be Fabian.
The next, I just have the name of the talk, so I don't have now the speakers. So if you can let me check. Okay. Yeah.
The second one, I think I'm assuming it's Fabian.
Yeah,
right?
it's me.
Okay.
So is everything working fine?
Yeah.
Yep.
Perfect.
So who's next?
Max, I guess.
Yes, I'm here.
Okay. Please, Fabian, stop sharing the screen.
How do I stop sharing just the screen?
Below, well, when you say share screen, there's an option that says unshare. It should be on the top of your screen, I guess.
Well, I can just share another screen, but I don't have a stop button.
Okay, let me check.
Ah, now it works. Okay, never mind.
Perfect. Then is that if you don't unshare the screen, I cannot. The other cannot share them. So, okay, the third one is Max. Okay, go ahead to test it.
The next one, who is
Okay, can you see it?
Yep.
Yeah, okay.
Okay, perfect.
Go one slide. Okay, perfect.
Okay. And
Ale
that
Alexandros is the following
Alexandros, I
one.
think.
Yep.
Yep.
Okay.
Here. You can see me, hear me,
Yep.
slides. Yep.
Yep.
Okay.
Perfect.
Cool. Then it's Jimmy again. He's all done, I think. He's good. And then Mike.
Mike.
Yeah. Should I share my screen or?
Yes,
yeah,
please.
Okay. So
it's working.
It's working?
Yeah.
Yep.
Fine.
Okay.
So
and now who's next?
Dominic.
I can see him. Ah, I know I can. Okay. Now I see.
Yes, does it work?
Yeah.
Yep.
Yeah, it's working. Thanks.
Thanks.
Thank you.
And
Okay.
then Chris.
Does it look good?
Yep.
Yes. It's all good.
Right.
Okay. Okay. Could you all turn your cameras? All of you. Yes, to take a photo before the session starts.
okay.
Pavel, if you could move a bit behind.
Let's behind. I start
Yeah,
to
like this.
disappear
And
into the
Chris,
background.
the camera, please. Okay. Smile. Okay. That should be it. So remember, please, to turn your mics off when the others are speaking. And for the questions, Pavel, you tell me, some people can raise their hands and some others can use the question and answer functionality.
I'll ask people to put questions on the Q&A and I'll read them out loud. I think it's the easiest way to
As
do
you
it.
as you want. If people can want to have the, as I said, the other option is that they raise their hands and then I give them audio. But as if you prefer that, that should be.
I'm just worried that 2 minutes is very short time. So, but
yeah, maybe
it's okay. If people complain, I can ask you to give them the mic. Just
okay then.
I think it's not
Yeah, use the. Just one thing for the audience to remember to use the question and answers, because it's not the same as the chat.
Okay.
Just that, and let me put one thing, and then are you? Is everyone ready? Then
Since the
I'm ready.
Since the previous session ended late, are we just shifting back time also, or starting on time? Because we're supposed to start 5 minutes ago.
Yeah, I would prefer if it just there's 50 people watching and.
yeah, and the truth is that I don't know. Maybe there's 50 people watching. Well, I think we.
I mean, either is fine with me. Did you want all the sessions to be synchronized and start at the same time?
That's I think that was the idea. So maybe if you are, I see that all of you are here. People are saying, please start and that. So I'll send I'll put the notification and then I'll. If you give me 1 second, Jimmy.
Okay.
And then.
Okay, so.
Okay, I think I can. Okay. Just put the. Okay, just put this announce and then you can. here, where it is. Can you see it?
Yeah, we can see your slide.
Okay, is that I've somehow lost the panel for Zoom. Okay. Well, then
we can start. Is that it?
You can start. Yeah.
Okay. So good morning. Welcome, everyone. Welcome to the reproducibility track. So my name is Pavel. I'm from the University of Lisbon. I really hope the time is convenient for you. I think some people are probably still in their pajamas, which is okay. No problem. It's the first conference you can.
I'm wearing pants.
Sorry. Okay, and so welcome to the reproducibility track. I'm very happy to be hosting it. It's something that I consider very important, and it's been neglected for too long. So I'm really happy that conferences now are giving some attention to reproducibility, and we had some very good submissions to this track. It was actually a big problem trying to choose which ones we're going to present at the conference. We actually asked for 2 more papers. That's why we have so many papers in this session, and not so many time. I'm sorry for already sorry. I say I'm sorry to the presenters that they don't have as much time as in the other sessions, but it was one way we found to get more papers. And so since we are already running late, I will not take very long, just give you some instructions. So there will be a 10-minute presentation. You have 10 minutes for your presentation, and followed by 2 minutes for questions. For the questions, I ask people to put them in a Q&A, and then I'll read them out loud, and presenters can answer them. You can use the chat for chatting, and in particular for applause. So you can applaud the presenters there. And just to remind you that we have a Slack channel where you can talk to everyone, talk to me, talk to the presenters and other authors, and share information. Okay. So for the presenters, I'll let them know when the time is running out. I'll have a timer ready, and I'll just rudely interrupt them if we don't have any more time. Okay. So we can now start and go to our first presenter, which is Jimmy Lin, presenting the paper from max score to block max 1. So, and very interesting, the story of how Lucene significantly improved query evaluation performance. That's a really nice subject. So please go ahead, Jim.
All right, good morning, everybody. Okay, so my name is Jimmy Lin. I'm a professor at the University of Waterloo, and I'll be presenting on behalf of my collaborators, Adrian, Robert, and Jim. All right. So the high-level question that we wanted to answer is, how can academic research achieve real-world impact? And so the way we thought we'd go about addressing this question is to look at successful real-world case studies. And this work is exactly one such case study. Now, let me set the context a little bit more. So the context is the top K retrieval problem. It's the standard ranking problem information retrieval. You have a big pile of documents. You want to retrieve the top K storing documents. K is usually relatively small with respect to some scoring function like BM25, right? So you can have the naive baseline, which is something like an exhaustive OR query evaluation document at a time that traverses all the postings. This has been known for decades. It's been known for so long that I didn't bother to look up a citation. The next sort of innovation dates all the way back to Turtle and Flood in 1995. The idea is to reason about the top K threshold using a technique called max score. You can say something like, well, this document isn't going to make it into the top K. We can just skip over the postings and not evaluate it. The next innovation after that is WAN, introduced by Broder et al. In 2003. And introduced some clever pointer movement that allowed further skipping of more efficient skipping of the postings list. And now we return to the subject of this particular study, BlockMax1, which is a paper that's written by Ding and Saul, presented in ECIR 2011. Okay, so just to get the terminology straight, the full sort of long name of the technique is one using BlockMax indexes, or BlockMax1, or I'll just say BMW for short. Okay, now the insight here is that Ding and Saul had is that you can improve skipping by storing block level metadata. And that was a really nice insight, and they did a really job in their paper sharing this technique with the community. Okay, now fast forward 8 years. So in March of 2019, this feature was introduced and rolled out as the default query evaluation algorithm in Lucene 8. And so basically every copy of Lucene 8 that's deployed now has this feature rolled in. Okay, so I'd like to take a pause now and like remark on how remarkable and how cool that is. Like, this is really a cause for celebration, right? This is academic IR research having an impact in the real world. Right. So I want to tell the audience a little bit more about this. In particular, I want to answer 3 questions. Right. The first question is, how did this happen? The second is, does it really work? And the third is, what are some lessons learned that I can quickly share? All right, so let's start with the first one. Okay, how did this happen? Well, the story dates all the way back to 2012 at the Lucene buzzword conferences, where Stefan Pohl introduced the Lucene community to the max score optimization in a presentation. Now, in addition to the presentation, there was actually a patch that was submitted that actually implements it. Right, so this is a Lucene issue 4100. Now, it was a working prototype, but alas, it required an index rewrite. And so it was unacceptable sort of patch to merge at that time because it traded off too much of the flexibility that Lucene offered. So in short, it was sort of like an idea, a great idea, but that was ahead of its time. Okay. And so sort of this idea lay fallow for several years, for at least 5 years. And 5 years is kind of a long time, right? And in the meantime, there were some important developments. For example, in 2015, Lucene finally got BM25. And with BM25 came natural score upper bounds due to the natural TF saturation effect of BM25. And so you could start to reason about score bounds for things like max score. Okay, so in 2017, Lucene got WAN merged into the mainline main trunk. And in 2019, all the features got rolled out. BMW got rolled out in the official distribution of Lucene 8. Okay, so let me move on to the second question. Does it really work? Okay, so we set off recreating the experiment of Ding and Saul from 2011. All right, so this was the basic setup. They were evaluating on the Gov2 collection, 25.2 million web pages, a standard IR test collection. They're evaluating top K retrieval, K equals 10, latency measured in milliseconds. For their queries, they use 1,000 random queries from Trek 2005 and Trek 2006 efficiency tracks. I emailed Thorsten, and he was kind enough to give me the exact queries that he ran. So those were the queries that we run also. All the experiments here were done with the Answerini IR toolkit using all default settings. So this is all reproducible from our website. Okay, so here are the numbers that are extracted from their original paper. And they evaluated 3 conditions: exhaustive OR, WAND, and BlockMax1. And this is the query latency in milliseconds. And these were our reproduced numbers. So we tried exhaustive OR, the pre-WAN BlockMax1 algorithm, and BlockMax1 using the conditions that are outlined above. All right, so hey, it works. right? So it works in a deployed system now. Okay, so a few more observations. We note that the magnitude of the improvement diminished, right? So Ding and Sol reported 18x and 8x improvement. In Lucene, it came down to more modest 3x. So we think it was because the Lucene baseline of exhaustive war was already somewhat optimized, already much better. And the other really interesting thing is that Lucene is still slower in absolute terms than the numbers that Ding and Sol reported. You know, this is being 9 years later and run on much better hardware, much more modern hardware. Right. So we would attribute this to lots of differences. So for example, Ding and Sol was a research prototype. Lucene was is a production system. It was C++ and Java. Lucene, because of its flexibility, has a lot of layers and indirection, which has an impact on its performance. Okay. All right, so I want to wrap up very quickly in this short talk with sort of some musings about lessons learned. Okay, so in sort of this whole process, we really learned that, you know, as you could expect, impact is hard, all right? And it takes a long time, right? So from 2011, when the paper was published, to 2019, when the feature was rolled out in Lucene, was a total of 8 years. And there are lots of hurdles for this. You know, there's breaks down into technical hurdles and social hurdles, right? The technical hurdles was this involved an invasive change and it broke backwards compatibility. And so sort of took a long time to work its way into a production grade system. The other was a social hurdle. This was not actually a completely transparent swap. It actually changed the behavior of the hit counts. So, so the number of hits that were reported is no longer accurate. And so all the people that depended on that for analytics needed to do something else. And there had to be some workarounds developed for it. So technical and social hurdles as well. Now, as a result of this impact and how long it takes, we have a few observations, right? So we note that the improvements really must be worthwhile in order for their way to make it into sort of real world practice. You know, improvements of, 5%, 10%, even 50%. And man, we're really looking for multi-fold improvements of performance in order for the effort to be worthwhile. And also, as a result of this, technology kind of skips generations. Right, so Lucene skipped all the way from an optimized version of exhaustive OR past max score, past WAN, all the way to block max WAN. That's like 20 years of IR technology, right? Okay, and finally, let me conclude with some thoughts, right? So let's just go back to this basic question. How did Lucene get BMW, right? Well, the obvious answer is, well, the developers read the paper and decide to implement it, right? But this was really a fateful choice, right? So what if they hadn't, right? So what if they read the paper, decided to ignore it? What if they didn't know about the paper and implemented, something else that addresses the core problem, the core underlying problem? Well, in this case, we wouldn't be up here presenting a reproducibility effort, but we'd be up here presenting a compare and contrast different query evaluation algorithms, right? So popping up a level, right, in this chasm between IR research and IR practice, I think sort of the advice learning from this we have for the community is that, researchers should do a better job evangelizing their work and, and spreading their work and telling the world about it. And on the flip side, developers should do a good job reading the academic literature. And by the combination of those two, we can sort of move a little bit closer to bridging the chasm between IR, academic IR, and practical IR in the real world. Okay, that's all I have, and I'll be happy to take any questions.
Okay, thank you, Jimmy. That was really as fast as promised. So we have time for plenty of questions. So if you have questions, please write them in the Q&A. and I hope I'll see them on the Q&A. Nothing so far. Okay. Okay, so we have a question from Gabriel Tolosa. He says, thank you for the presentation. Have you any insights about how much save time corresponds to moving from MS to WAND, and how much to the blocked index representation? So
No. So the question is essentially about a ablation analysis separating out the block level metadata and the difference due to WAN, right? No, the answer is no. We haven't done that ablation study yet. We've been in discussions with the team and with other IR researchers about sort of going back and doing exactly those types of experiments. So since I have time, I'm going to add a little bit more detail here. The implementation in Lucene is not actually the implementation that Ding and Sol described as exactly they described. And so there's some technical differences, and we'd also like to go back and examine the impact of those design choices. They stem from the fact that Lucene has a much more flexible score ranking algorithm. So you can't just store the impact scores directly. You have to store the DF and document lengths to compute the score upper bounds.
okay, so any more questions? No questions from all the 63 participants. There's a nice comment on the chat if you'd like to check it, Jimmy, addressed to you.
I have no idea how to do that, but I'll read it later.
Okay. There's another question. We can take it. So Martin White asks, one of the issues about devs reading academic literature is that so much of the literature is firewalled and devs cannot subscribe to all relevant journals. So this is not a question, this is a comment that I should have read before typing it, but anyway, I'm not sure if this doesn't sound like something appropriate for the talk, but anyway.
Well, I think the paywall issue, most publishers do allow authors to post their preprints, right? At the very least, preprints. And so this is something that the academic community should think about more, people that are unable to read our works.
Yeah. Okay. So any more questions? So I think we're done. Thank you very much, Jimmy.
Okay, and I'll be back for another talk later.
Yeah. We'll see you in a few minutes. Thank you. And I think we can go to our next presenter, which will be Fabian Schlitzky.
Yes. Okay, so
thank you, Fabian. So Fabian we'll talk about the influence of random walk parameterization on graph embeddings. We're looking forward to your talk. Please go ahead.
Exactly. So thank you, Pavel, for the introduction. My name is Fabian Schlitzky, and I'm a master's student at the University of Passau, and I'm going to present our paper, Influence of Random Walk Parameterization on Graph Embeddings, which I developed together with Jörg Schlotterer and Professor Michael Granitzer. So onto a small background. Just a reminder how graph embedding with random walk works. So we have an input graph, and starting from every node, we sample random walks of a specific length, and these are then fed into the skipgram model, from which we can retrieve the learned embeddings. And just a brief overview of the skipgram model, most of you should be familiar with it, but I will introduce it anyway. So it was introduced by Miklov et al. In 2013 for creating word embeddings initially, and became famous under the term word2vec. So it's a neural network with one hidden layer, and we're conducting a fake task on it. So instead of training the model and then using it, we are training it and using the weights between the input and the hidden layer as the trained embeddings. And for embedding graphs, we use these sentences or these random walks we just created as sentences, and instead of predicting a context word for a center word, we are predicting the context nodes of center nodes. So each node in the graph is then one word in the word-to-vec terms. So Node2Vec was introduced by Grover et al. In 2016, and they introduced 2 parameters to guide the random walks through the graph. On this figure, you can see where we currently are in the random walk. So the red node is where we just came from, and the green node is where we currently are. And the probability of returning back to the node we just came from is modified by 1 through p. And the probability of moving away from the neighborhood of the node we just came from is 1 through q. So by this, we can interpolate between the 2 extremes, depth first search and breadth first search. So the goal of Node2Vec is to preserve both community structure and structural rows in the embeddings. Community structure is about proximity in the graph. So nodes that are close together in the graph should also be close together in the embeddings. And structural rows are, for example, hubs or bridges. So hubs are connecting many nodes and bridges are connecting subgraphs. So we introduced 2 additional random walk parameterization strategies. The first one is jump probability. The parameter j is the probability of randomly jumping to a different node during the random walking. So it essentially adds noise to the walks by walking over otherwise non-existing edges. So with j equals to 0, it's an unparameterized random walk, similar to deep walk. And with j equals to 1, it's a random walk which pays no attention to the graph structure. And yeah, everything in between can be set. So the second strategy is hub attention. The general definition what a hub is a node with a degree that greatly exceeds the average. Our turn-on is that every node where the degree is larger than the mean degree and the plus the standard deviation of the degree is a hub, and this works quite good in practice. So similar to Node2Vec, we modify the transition probability. If the neighboring node of the current node is a hub, we modify it by 1 through h, and otherwise we don't modify it. So essentially h controls the likeliness of revisiting or visiting a hub. Then the experiments we conducted. The first one is a visualization task on the rather small Lee-Maserati dataset. So we cluster the embeddings retrieved from the skipgram model with k-means and assign a node color based on the cluster, and then analyze these visualizations. The second task is a node classification task on the block catalog dataset. So we averaged the macrophone score over 10 random 50% splits. And this is actually how the experiments which were also conducted in the Node2Vec and other similar research papers. So this is quite a good basis of comparison. Then onto our results. On the left, you can see the figure taken from the Node2Vec paper, which we wanted to reproduce. So the top graph, according to Node2Vec, embeds community structure with the variables P1 and Q0.5. So we are moving away from inner nodes outer in the graph. So more of a depth first search. And this was actually perfectly reproducible, and we got the exact same result as you can see on the top right. The embeddings also represent community structure. The bottom figure of Node2Vec is according to Node2Vec representing structural equivalence. So you can see that mainly bridges are marked blue. But we had no luck by using the parameters P1 and Q2 of reproducing it. The embedding still showed community structure instead of structural equivalence. And no matter what we tried out, even grid searching all parameters, we never found any that were embedding then structural equivalence. The embeddings always represented community structure. So a discussion on this reproducibility. As you have already seen, embedding structural equivalence was not possible using the given methods. This might be the reason because the skipgram model is actually not designed to embed structural equivalence, but to predict and therefore embed neighboring nodes. So nodes that are closely together in the graph are also embedded closely together. due to the random walk fashion. So we also have to consider the context window of the skip-gram model. The global element of the exploration is not as relevant as Node2Vec suggests, as only the nodes within a context window are relevant for learning the embeddings. So as an example, we have this walk through the graph where we are currently looking at the center node Fox. So only the words or nodes quick, brown, jumps, and over are in the context window and relevant for the current walk. And independently how the walk continues after that, it doesn't affect this node as much as the context window limits the context nodes always to the area around the node. As a random walk always traverses through the nodes in the neighborhood and then through the current node, by modifying the global random walk is not that effective. So then onto the visualizations on the jump probability. It's quite what you would expect. By adding noise, the embeddings constantly get worse. So we are getting no benefit, but we can see that 10% noise doesn't impact the results as much as you could expect. Even more on the smaller Les Miserables data set, but on the other data set, you will see that it's not that affecting that much. So the hub attention visualizations, on the left, you can see the result using the hub attention algorithm with a value of h equals to 4. So we are moving away from hubs, reducing the probability of visiting hubs, and exactly the same result as we got with Node2Vec regarding community structure. So onto the node classification task. First, we reproduced the results of the Node2Vec paper. So by using p equals q equals .25, they got their best result of 27.25. We got this value. It's a little bit higher than the one they reported, but still with a margin of error. But also they reported their results for deep walk. And when setting p equals q equals 1, it's actually just an unparameterized random walk. So it's deep walk essentially. But our value was largely higher than their reported value for deep walk. They reported 21.10 and we got at least 5 points higher. The jump probability is the same result as in the visualization. So within it constantly gets worse as higher the jump probability gets, but it's still performing quite well with 10% jump probability or noise, as we can also call it. So we still get a score of 26 compared to the deep walk score of 26.46. So that's better than you might expect. And the hub attention was actually our best performance overall. So we can get consistent results from H1 to H10. And actually our best result is 27.5. It's better than the Node2Vec score, but only 25 points better than Node2Vec. So this could also be explained by the random factor. So what conclusion can we draw from this? Node2Vec promises embedding both community structure and structural equivalence, but doesn't deliver on the structural equivalence part. So at least on our data sets with our modifications, random walk parameterization doesn't improve much. It's questioning whether the minimal improvement over pure random walks is worth the effort in computation. So the deep walk paper actually reports a score of 27.3 on the block catalog dataset when we are using more but shorter random walks, which is on the same level as our best result without any random walk parameterization. So it's a question whether the additional hyperparameters introduced only increase the difficulty of finding the right parameters instead of improving the results as much. So in our side of view, the increased effort of parameterization of random walks is not worth the time and computation. So yeah, that was basically my talk. These are the references. And if you have any questions, feel free to ask.
Okay, thank you very much, Fabian. So any questions? Just waiting for questions to show up. Okay, a question from Evgeny. Did you play with the size of the context window?
Yes, it didn't really harm the results if we made the context window smaller than what we just used. But with an increasing size of the context window, the results tend to get worse because it includes too many nodes in the context nodes. So there's no really differentiation between the different nodes then. But when trying to reproduce the structural equivalence part, we also included the context window with the grid search. So yes.
Any more questions? A question from Rowan. Nice talk, he says. Could you please comment on potential alternate random walk parameterization strategies? Is it possible?
So we didn't came up with other parameterization strategies besides the two we also introduced, but there might be ones that could work better, but they have to, in my opinion, have to move independently of the graph structure to embed different structural parts of the graph. So when we're using random walks where we constantly are not skipping anything, but walking from node to node, you will always embed the neighbor around these nodes, so the area around the nodes, instead of embedding like structural equivalence. I hope that was understandable.
Yeah, I think so. Okay, so I just got another question, but I think we have to move on. I'm sorry.
I could answer it in the chat. So
okay, so okay, I'll put it. So I'll ask the person who made the question to put it in the chat or in Slack, and Fabian can then answer it.
Yeah.
Sorry about that. Thank you very much, Fabian. That was really interesting.
Thank you.
Let's then go on to our next speaker, Max.
Yes. Okay, can you see my slides?
Yes.
All right, so then I start. Hello and welcome from my side. I'm Max Berndorf from LMU Munich, and I'm going to present joint work with my collaborators Evgeny Fehrman, Valentin Melnichuk, Volker Tresp, and Thomas Seidel, which is titled Knowledge Graph Entity Alignment with Graph Convolutional Neural Networks, Lessons Learned. Okay, so let's start with dissecting the title. What is actually a knowledge graph? A knowledge graph is a flexible way to represent factual knowledge in the form of a multi-relational graph, where the nodes represent entities and edges the relations between them. So you can see an example on the slide. In the task of entity alignment, which is a well-established task, we are now seeking, we're having two of these graphs, and we would like to identify common entities among them. And this task is relevant to the IR community, since when we want to retrieve information, we can only have as good results as we have data. So enriching our data by different data sources is always a desirable task. Regarding our motivation, so why did we write the paper? Actually, we started, we had an idea how to improve entity alignment with graph convolutional neural networks. And we were looking for a simple yet strong baseline and came up with one work which is named GCN Align. And initially we had quite some trouble to reproduce the results. And so therefore we would like to spare this trouble from others. Moreover, we also want to assist people in starting in the field of, or getting into the field of entity alignment. And third, we also conducted extensive experiments which provide a strong baseline setting on numerous commonly used benchmark datasets. So I'd like to summarize our contribution as follows. So we provided a description of benchmark datasets and variants thereof. We discussed the implementation details of this GCN-based method GCN Align, and elaborate also on some code-only features. And we also conducted an extensive experiments with ablation studies, where we identify the importance of different hyperparameters and found strong settings for various data sets. So let's start with the data set. The paper we investigated, the GCN line, evaluates on a data set which is called DBP15K, which was created from DBpedia. And it was created by the authors of a method called JAPE. And while they did not mention in the paper, their co-published code shows that they use a different and smaller variant of the data set. So if you compare the in the table these two sizes, you can see that the number of entities is largely different, approximately 1/3 to 1/5 in the size. And actually, we found that most works using this data set actually report the statistics of the larger data set, but evaluate on the smaller variant. And this is relevant since the task gets easier if there are fewer candidates to align to. Okay, now I'd like to roughly introduce the model of GCN-Align. As most state-of-the-art methods, this GCN-Align is built upon graph neural networks. And very roughly speaking, it learns embeddings for each entity and then enriches these embeddings using transformed embeddings of the neighboring entities. So you can think of it as some sort of message passing. You have the node embedding, and it receives messages from all its neighbors, which contain information about them. So afterwards, you have a description of this neighborhood. Going more into the implementation, there are some details. So the first detail is that GCN-Align compresses this multi-relational graph into a single adjacency matrix by a weighted sum of the individual relations adjacency matrices, and they are based on a relation popularity. Also, this final node representations, which got enriched, are then compared using L1 distance, and we use a margin-based loss function to train this. Then there are some additional details from the code which are not mentioned in the paper, but which we found out are also quite important. The first is that the node embeddings are L2 normalized before the message passing happens. Then the second one is that, this is quite surprising, that the embeddings are not transformed for the message passing. So in the message passing phase, we do not have any weight coming in. And then the third one is that the node embeddings are initialized randomly with a specific variance depending on the negative square root, or inversely proportional to the square root of the number of nodes. So we conducted also extensive experiments, and in the initial experiments, we found out that the most important hyperparameters are the usage of transformation weights, where using this transformation weights actually hurts the performance on most data sets, and the variance of the random embedding initialization, where we studied a different and simpler variant and found that the simpler variant actually performs better than this this unexplained term of proportional to the square root of available nodes. And we were also able to improve the results quite significantly on, for instance, on this data set, DBP15K, this smaller variant. We could improve the hits at one from approximately 36 to something to 45%. Okay, I think I was a bit fast, but nevertheless, I want to advocate some additional material which we provided. We provide the code to reproduce our reproducibility study on GitHub. We also have created an additional technical report on arXiv, which, in addition to what is already in the conference paper, also provides links where to get this different variants of the data set from, also includes more metrics, so also mean rank, mean reciprocal rank, hits at k for different k values, and also the exact hyperparameter configurations found for each data set, subset combination. So you can use them as a starting point for your own research. And last but not least, we also have a new work on evaluating entity alignment, which you can find under the following link. Okay, so these are my references. And then I would like to thank you for your attention, and I'm open to questions.
Okay, thank you very much, Max. I'm really not an expert on entity alignment, but I'm an expert on making mistakes. So thank you very much for your noble intentions of stopping people from making further mistakes. And that's, I think your paper is really representative, good representative of what reproducibility papers should be, I think. So thank you.
Thank you.
So as before, please put your questions on the Q&A if you want to ask Max some questions. Waiting for the questions. I think the questions take some time to appear here on my dashboard. Or people don't have any questions, I think.
Yeah, you can also ask them via Slack or later in the chat, also by mail, however you like.
So we do have some time because your presentation was really fast and clear, apparently, because no one has any questions. So I think no questions then. So we can, well, if you do have any questions later, you can, as Max has said, you can put them in the Slack channel for our track. I'm avoiding saying the word reproducibility again because I mess it up. But anyway, if there are no questions, thank you, Max. Thank you very much for your work. And we can go ahead to our next presenter, Alexandros. Are you there?
Yep.
Okay.
I'm here.
And we'll talk about word embeddings now. So whenever you're ready.
Yep. Hello, my name is Alexandros Bamboulidis, and I am a researcher at RSIFK. And I will present to you our work together with Luca Papariello and Mihai Lupu on reproducing document representation methods and their use in the tasks of clustering, classification, and retrieval. I will start by presenting the document representation methods that we reproduced, then the experimental workflow we followed, the experiments we conducted and the results we got. And finally, I will conclude by recounting the difficulties we faced in reproducing these methods. So the research question is, in general, is that how to combine individual word representations in order to obtain high quality document representations. And to do that, we investigated different representation methods and tested their quality in the tasks of classification, clustering, and retrieval. The methods, the document representation methods that we investigated are TF-IDF, which always serves as a baseline for more advanced techniques. Then LSI, which is a linear dimensionality reduction method. And essentially it is singular value decomposition in linear algebra, but it is not a learning algorithm. Then we have LDA, also a dimensionality reduction method based on topic modeling. It is a learning algorithm, and each document is expressed as a combination of various topics. Then we have the continuous pack of words, CBAU, which is a word-to-vec, a word embedding method in the CBAU architecture. There, for each word, there is a numeric representation of the word that is a vector, and the document representation is obtained by averaging these word vectors. Then we have the paragraph vector methods, PV, also known as doc2vec, which is a document embedding algorithm that builds on word2vec. It creates a numerical representation of a paragraph or a document, regardless of its length, that is the number of words. We investigated both its implementations, distributed BAU and distributed memory. Finally, we have the feature vector methods, FV. these methods are based on the Fisher kernel framework, and this framework offers the option to aggregate word appendings to create fixed length representation of documents. We investigated both these its implementations, FV Gaussian mixture model and FV von Mises-Fisher, VMF for short. Now, of all these, the most recent advanced developments are the FV methods. First came GMM, and then came MOVMF. And in the paper that it was introduced, the VMF method, it has been shown that it is capable of outperforming the existing baselines. And we followed the exact experimental workflow of this paper, and we introduced additional parameter scans. For the TF-IDF, we use the existing implementation in scikit-learn. For LSI, LDA, CBAO, and PV methods, Jensen's method implementation. But for the FE methods, there was no implementation available anywhere, and we had to implement them ourselves with the help of the libraries of scikit and Sphere cluster. And for the retrieval experiments, we used Lucene, the latest version of Lucene. And yeah, so the experiments consist of 3 phases. First phase is the text processing, which includes tokenization and stop word removal. Then we create a vector representation of the documents for each of the aforementioned methods. And third, the actual experiments of classification, clustering, and retrieval. For the classification experiments, we used logistic regression, as in the original paper. And we did a parameter scan of the inverse regularization strength. And we tried different number of training epochs and different dimensionalities of the future vectors. We used 2 datasets, the subjectivity dataset, consisting of 10,000 instances. And the goal here is to classify sentences into subjective or objective. And then on the sentence polarity dataset, with 10,000 instances, to classify a sentence into positive or negative. Here are the results of the classification in a 10-fold cross-validation setting. On the subjectivity dataset, we can see that every method, almost every method, achieves a similar performance when properly tuned with the inverse regularization, I mean. But for the sentence polarity dataset, it is surprising to see that the simple TF-IDF outperforms all the other methods. Then we have the clustering experiments. For the clustering experiments, we use the K-means algorithm. And we experimented once again with different dimensionalities on the 20 news group dataset, which consists of 20,000 documents grouped into 20 classes, which also serve as the clusters in the experiments. Here you can see the results of the clustering. What you can see here is that the lower dimensional methods perform better than the higher dimensional ones, and that the FE methods significantly underperform. So the bottom line is the lower dimensional, the better. And then finally, we have the retrieval experiments. We did the retrieval experiments on the Trek robust O4 dataset. We experimented with 3 topic processing ways. The combination of title and description provides the best results. Naturally, BN25 serves as a baseline in this task, and we performed a parameter scan for it, specifically K1 from 0 to 3 and B from 0 to 1 with a 0.015 step. And the other models were combined with BN25, essentially re-ranking the original BN25 results. To do that, we normalized the BN25 scores to 0, 1, and the final score for each document given a query is calculated with this formula, which basically states that BM25 contributes 80% to the score, and the other model contributes 20% to the score. Here you can see the mean map and P at 20. It is quite obvious that BM25 is quite hard, very hard to beat baseline. And to conclude our reproducibility experience, the fact that there was no source code available for the FV methods and that certain formulation and implementation details were omitted in the original MOVMF paper led us to putting significant effort in trying to reproduce the method. And in the end, we actually were not able to confirm the findings of that paper. You may find the source code here, and if you have any questions, do not hesitate to ask here or in the Slack or email. Thank you.
Okay, thank you very much, Alexandros. So we're open for questions, and we already have a question from an anonymous attendee. So he or she says, I am not an expert in the area and want to ask a general question. Are these methods still relevant in the time of GPT-2, BERT, and the pre-trained models?
Well, I'm not an expert also, but I can say that we would not benefit much from BERT because of the small data sets that we have. We can see here that the data sets are only 10,000. And to apply BERT, we would actually need more instances. And in addition to this, I believe BERT also has a limit on how many tokens it can take. It's about 500, I believe.
Okay, but can I just, let me add something. So you mentioned the size of the data sets. So do you think that also had an influence on your results? If you had larger data sets, maybe you could have gotten better results from the...
Yes, so to clarify, we follow the exact same workflow of the original paper. And yes, I believe it does have an influence because while we reported a similar performance of MOVMF, the novel method here, but then we actually have this surprising result of TF-IDF, and we used exactly the same implementation as the original paper, which gives a clue that probably the workflow, the original workflow, has flaws, and that most probably is attributed to the instances of the dataset, the small number of instances in the dataset.
Okay, so we have a follow-up question. It's an anonymous attendee, so I'm guessing it's the same person. Isn't the small size of, well, I think this is basically more or less the same thing I asked. Isn't the small size of the data set the reason to use a pre-trained model? Related to what I asked.
So, I guess, yeah, it could be. Yeah. But once again, we follow the original workflow.
Okay, so but anyway, that would be a nice paper for next year's reproducibility track, comparing the BERT models. Well, thank you very much for your presentation. I also liked it a lot. I have this guilty pleasure of listening to sentences like BM25 is very hard to beat, or TF-IDF was better than everything else. So that's the reason why this track exists, I think. And thank you very much.
Thank you.
So for our next presenter, which will be Jimmy Lin again, and also another perfect fit for this track, reproducibility as a process. Jimmy, take it away. I think. Are
we good?
Yeah, we're good. We're good.
Okay, good. Hi, I'm still Jimmy Lin, and I'm still a professor at the University of Waterloo. And this is work with my postdoc, Chan Zhang. Okay, so the story begins all the way back in ECIR 2016, where a group of us wrote this paper, what we call the open source IR reproducibility challenge, right? And so the claim here, and this is the claim taken directly from the abstract, that as a result of our work, the product is a repository that contains all the code necessary to generate these competitive ad hoc retrieval baselines. So that with a single script, right, you have the collection, you run a single script, anybody can replicate all these results, all right? And so for this work, we decided to put this claim to the test. All right. So late last year in 2019, we had the idea of, okay, let's come back and let's try to rerun all the code that's in this repo. Okay. And this work is reporting the results of what happened. Okay. So before I get to there, I think it's natural to answer this question, like, who cares, right? Why is this interesting? Why do we want to go back and run old dusty code? Okay, and well, the answer is in the title of our paper. Reproducibility is a process, not an achievement, right? So in a typical IR reproducibility effort, it's sort of like a snapshot of a time in place achievement, right? You do this, it usually has two results. Yay, happy, we reproduce a result, or we have to scratch our head and figure out what happened. Right? But it's actually more than that, right? So every IR reproducibility effort usually results in some computational artifact that gets created, right? And so a natural question is, are these artifacts going to be still executable over time, right? And that's exactly the question that we tackle, the replicability of IR reproducibility experiments. And here we're using the definition of the two terms exactly as ACM defines them in a recent working task force draft, right? So reproducibility is recreating a result using an independently developed artifact, right? An artifact that's independent from the ones developed by the original authors, right? Whereas replicatability is to recreate a result or an existing result using an existing artifact, right? Just taking code and rerunning it, seeing what happens, right? So this is the focus of of this particular work. Okay, and so I still really haven't answered the question of, why would we want to do this? I can give you at least two compelling examples, the reasons, right? The first is that we want baselines to be stable across relatively long periods of time, right? So artifacts that produce baselines should be replicable by lots of people. Right? There's also the issue of, computational contexts are always changing, and it'd be nice to re-examine findings with respect to these changing computational contexts. Right? A simple example is, algorithm A is faster than algorithm B, but that was on spinning hard drives. Now we have SSDs. Well, does that change things? Well, we have to go and rerun the code to see what the impact of this different context is. Right? Okay, so now going back to this paper, the setup I'll just briefly describe is once again the GOV2 collection, 25 million web pages. These were topics for 701 to 850 from the Trek terabyte track from 04 to 06. Standard top K retrieval with K set to 1,000 in this case, and the metric is average precision. Okay, so the claim made by this paper within the repo is that there is a single .gov script associated with every system. And the claim was, you'd run the script and it would generate all the results from soup to nuts, right? Indexing, running retrieval, et cetera, et cetera, et cetera. Okay, and so there were 7 systems that participated in this effort back in 2015 when the work was done, and 13 runs, and this is what we'll be examining. Okay, so here are all the runs running down my left-hand column here, and here are the conditions. Run successfully, output matches exactly what we'd expect in terms of average precision. Run successfully, but output different, and then fails to run. All right. Okay, so we had an old server lying around. This was purchased in spring of 2017, runs Ubuntu 16, Java 1.8, GCC 5.4. Okay, and here were the results running in on that old server in late 2019. Okay, so 5 of the 7 systems ran successfully, but only 2, Attire and Terrier, actually produced the same score. There were a couple other systems, Indri, Jas, and Lucene, that ran successfully, but gave average precision that were slightly different than what was reported in the paper. Okay, so this is the old server. We also actually had a new server, a server that we just bought last summer, runs Ubuntu 18, Java 11, and GCC 7.4. So much upgraded software versions. And we try to run the code again. And this was what happened, right? So out of all the 7 systems, only 1 system ran successfully and produced the same score. Okay, so kudos to Terrier. They get the yay minion. Now, for everybody else, it's basically the sad face minion. Okay, now you might be wondering, why? What happened? Okay, so I'll briefly go over all the failure conditions. Okay, so MG4J was easy. The tarball no longer existed on the web. So we had a broken link. We couldn't get access to the artifact. And so it failed right from the get-go. All right. With Attire and Jas, we ran into compile error. There were some namespace clash issues between C++ 11 and 17, and it didn't even compile. By the way, this is on the new server, just to be clear. And Lucene, between the old and the new, what it did was that particular version of the Lucene exploited an undocumented feature in Java 1.8 that was no longer there in Java 11, so it didn't work. Indri gave a seg fault, couldn't figure out why, and we just had a lot of trouble debugging Galago. Okay. All right, so just very short talk, can wrap up here, right? What were the lessons learned? Okay, that this is really, really, really hard problem, right? Right off the bat, there were just 2 broad categories of problems: link rot, software not existing anymore, and then software incompatibility issues. Okay, and I think this is relatively unexpected. It's hard even if it runs. Right. In particular, I mean, taking the output of the logs that these scripts are generated, and a lot of the systems did copious amounts of logging, and matching up the figures that were reported in console with the figures that were reported in the paper was a really, really laborious process. And sometimes we just couldn't figure out where the numbers were gotten from, where the numbers came from. Right. And so perhaps for the first problem, better packaging via Docker might be the solution. And perhaps for the second problem, this really says that, for better documentation, this move towards notebooks and the whole idea of literate programming might be moving everything into the field in the right direction. Okay, now I'll end up with this thought. So at ECIR 2019 last year, a group of us got together and organized the 2019 version of the open source IR replicability challenge. And it'll be interesting to come back in 2023 and rerun those experiments and see if the code still works. And perhaps I'll be talking about this at ECIR 2024. Okay. That's all I have. I'll be happy to take any questions.
Thank you, Jimmy. Thank you very much. That was very interesting. I should say that this track should probably be called reproducibility and replicability, but since I have a hard time pronouncing both words in a sequence, we decided just to cut it short and be reproducible. So let me give you the first question from Paulo Almeida. So part of this age-old discussion of backwards compatibility, pros and cons, maintaining Frankenstein code and DevOps, what's the way forward?
the facetious answer is the first step of recovery is admitting you have a problem. And I think this is sort of the first step. And so we have a problem. I think Docker might be a step forward in being able to create nice bundles of software that preserves the existing, the stack and snapshotting the stack at the time that it runs. And so I don't know, but the real answer is, we'll really have to wait and see.
So can I add, let me add a follow-up. So Docker seems like a good idea. And the second problem you mentioned, really interesting, that it's a you had a hard time getting the values from the logs of the. So do you think, many conferences now are asking for the code and the data. So do you think maybe conferences could be more restrictive in how they want the code to be presented? And for example, asking for notebooks that show the same output as what they are putting in the paper or something like that. That could be in the conference rules. Do you think that's a way forward?
So there's been a sort of a long discussion that goes back for a long time in the IR community about something like this issue. And I don't think a top-down sort of reinforcing the rules is going to work, because it's just going to drive people away. I think what's more valuable is sort of a bottom-up, community-driven effort, like the OSIRC effort that a group of us had organizing. And so I think it really comes down to sort of building critical mass and community that cares about this enough to follow these community norms. So yes, I think those are exactly the right things to do. Notebooks, Docker, things like that. But I would not advocate for a top-down approach.
Okay. So Paulo Almeida is following with another question. He says, for this question, I would suggest unit tests, integration tests. Would it work in science?
If you could get your students to write unit tests, it might work. At least sort of personal experience in my own group, there's always a balance between moving fast and going back and write unit tests. And so my sort of general philosophy to this is sort of the baselines need to be rigorously tested. But the sort of the advanced features that we're working on, I'm sort of less insistent on.
Okay. Okay, thank you very much, Jimmy. Thank you for both your presentations. And I think we can go forward now to the next.
Okay, and you'll hear from Chris. You won't hear from me a third time. You'll hear from Chris for the final talk.
So next presenter, Mike.
Yeah, hi.
He's going to talk to us about the effect of near duplicates on evaluation. You can go ahead when you're ready, Mike.
So I should be ready to go. Can you see my slides?
Yes.
Okay, so thank you. Yeah, I would like to talk about the impact of near duplicates on the evaluation of search engines. My name is Mike. I am a PhD student, and yeah, this is a PhD student in the first year. So this is my first paper that I have published. And let us assume that we have such pairs of near duplicates in our collection, and that both are relevant for some information need. Then we have a problem in the evaluation of retrieval systems, because systems can obtain multiple rewards for showing the same document. And we believe that it is important to address this problem, because the Wikipedia article in this example has over 14 near duplicates in the Clue Web 09, and all of them are judged as relevant for topic 194. There is a possible solution to that problem, and it dates back to 2005. There's a paper by Bernstein et Zobel with the title redundant documents and search effectiveness. And in that paper, Bernstein and Zobel proposed the so-called novelty principle. This novelty principle states that a document is irrelevant if it is content equivalent to a document the user has already seen in the results. And let's consider the novelty principle in the context of our example. The application of the novelty principle causes that the first document remains relevant, while the second document becomes irrelevant. And that is quite reasonable because the user would have seen the same document earlier in the ranking. And with that novelty principle, or Bernstein and Zobel conduct a study with that novelty principle on the terabyte track from 2004. They use two steps. First, they identify such near duplicates, and after they have identified near duplicates, they compare the official evaluation in terms of mean average precision with the evaluation according to the novelty principle, again with mean average precision. They have several interesting findings. For example, they showed that 60.6% of the relevant documents are near duplicates, and that mean average precision decreases by 20% in average for the submitted systems. So there is one thing that I want to highlight, namely that the study of Bernstein and Zobel is 15 years old and many things have changed in the meantime. So for example, sometimes nowadays we use larger test collections like ClueWeb 09 or ClueWeb 12. Sometimes we use smaller test collections like in Common Core 2017 or Common Core 2018. So and evaluation measures also change. For example, the use of mean average precision is discouraged in the meanwhile. And yeah, such stuff changes. So it is a quite interesting or a quite good point in time to reproduce and expand this study by Bernstein and Zobel. And we reproduce it on the terabyte 2004 track and choose 10 another shared tasks with a similar ad hoc retrieval task to expand it. And basically, we follow the approach of Bernstein and Zobel and identify near duplicates within the judged documents of the considered shared tasks. I'm not sure if I should remove that. Okay. So for the 11 shared tasks, we identify near duplicates in the judged documents. And we apply the same steps to normalize documents as Bernstein and Zobel did. And after this document normalization, we choose a near duplicate threshold to ensure that near duplicates are content equivalent with a very high precision of 95%. And with that setting, we can reproduce the reported distribution of near duplicates within terabyte 2004 quite well. So we can reproduce that fine. And so we can now expand to near duplicate detection, the near duplicate detection to offer shared tasks as well. And the figure below reports the proportion of near duplicates within relevant documents for all 11 shared tasks under consideration. We see that all tracks have some redundancy within the relevant documents, and some shared tasks, for example, the WebTrack 2012, even have topics with over 70% near duplicates within the relevant documents. And that is quite a good motivation to continue our study. So now that we have the detection of near duplicates, we can continue and compare the traditional evaluation with the evaluation according to the novelty principle. The first important point here is that we can reproduce the comparison that is reported by Bernstein and Zobel quite well. And I have no really the time to go into the details, so I only sketch that we can reproduce the plots that are published by Bernstein and Zobel nearly perfect with our pipeline, as you can see in this figure. So the right plot is by Bernstein and Sobel, the left plot is our reproduction. And the second important point, and I think this is quite important, is that we may have identified a problem with that novelty principle. So let us assume that we have a large group of near duplicates which are all judged as relevant. And we have also a ranking that does not retrieve any of the documents from that retrieval equivalent group. So in that case, according to the novelty principle, all near duplicates from that group would remain relevant because the ranking does not retrieve any document from that group. And we think that this behavior contradicts the novelty principle because in fact only one document from that group should remain relevant. So, and if we fix that special case in our evaluations, we call that the novelty principle with global manipulation of judgments. So let me now highlight some parts of our comparison between the traditional normalized discounted cumulative chain and NDCG according to the novelty principle. In that evaluation, we simulate that participants have removed near duplicates. That means we simulate that participants submit results according to the novelty principle. We also apply this global judgment manipulation because we believe this combination is the most realistic scenario for such a comparison. We report the changes in NDCG scores and see that for terabyte 2004, the application of the novelty principle causes the NDCG scores to slightly increase by 0.3%. And that happens because of the global judgment manipulation. With local judgment manipulation, we don't see that. So with local manipulation, the scores slightly increase in all cases. So at the same time, NDCG scores for example, for the WebTrack 2012 dropped by around 12.4%. And we also study the induced rankings of systems and report the changes to that system ranking in terms of ranking correlations. We find that the WebTrack 2010 has a really low correlation around 0.6. And if we only look at the 5 best performing systems, that correlation even decreases to 0.3. That means the novelty principle causes the ranking of systems to change. And we think that such a low ranking correlation is a cause for alarm. So I just would like to give you some main takeaways. One thing is that almost all considered tracks are affected by near duplicates. Maybe there's one exception, the Common Core 2017, but in all other cases we can see effects, and from participant side, this can also be a problem sometimes. If you also think that, for example, the scores that I have reported or the changes that I have reported are some kind of low, that is also no problem. If I change slightly some parameters in our evaluation, then the impact of near duplicates would increase. For example, if I compare mean average precision with mean average precision under the novelty principle, the impact of near duplicates increases. Or if I apply the local judgment manipulation instead of the global manipulation, then also the impact of near duplicates increases. And there's another important point to mention, namely that in the current situation, if you participate in a shared task, then you should not filter near duplicates, because if you remove near duplicates, you always get a loss. And in our study, we see that systems get a worst case loss between 8 and 53 ranks in such a system ranking. So that are my main takeaways. I finished. So thank you all, and I would be happy to answer some questions. Yeah.
Thank you very much, Mike. And first of all, congratulations on your first paper. Too bad you couldn't travel to Lisbon, but it's still part of a good experience. So it's open to questions. If the attendees would like to put some questions in the Q&A. And while the questions arrive, I also have some comments, questions. So first of all, I think this is a really interesting problem. I remember having this problem in my PhD thesis, which was long ago. And I believe it's a problem that's mostly ignored in research. Just to make something clear here, when you say in this last slide, when you talk about the current situation, what you say an obstacle, you ask a question, an obstacle to progress. What do you mean by being an obstacle to progress?
Yeah, I mean the following. If you build a search engine, removing or filtering the duplicates should be a matter of course. So I mean, search engines should remove near duplicates. If we look at the first example where we have 13 near duplicates of this Wikipedia article, no one would like to scroll to page 4 on Google until those near duplicates are away. So so that's the problem. What I would mention is that if you remove near duplicates, your system is evaluated as worse or gets a worse evaluation score.
Mm-hmm.
So for example, if we have one system and the system produces a good result but filters near duplicates, it is maybe worse than another system. So that's the point here.
Okay. Oh, thank you. So any more questions from the audience? Okay, so we have a question from Donna Harmon. Do you think there's an acceptable standard way of removing near duplicates?
Okay, that's a good question. I don't think that there is a standard way because I think the near duplicate or the content equivalence definition is dependent on the domain. So if I have some medical stuff, there might be small changes in some words really make a really big difference, but yeah, for general web text maybe not. So I don't think that there's a general one fits all solution for removing near duplicates.
Okay, let me also follow with another question. Do you think that's a problem that should be solved by people making the data sets or by people making the experiments?
That's also another good question. I am not sure because I know that making such a shared task is a huge amount of work, and deduplicating such large data sets like ClueWeb 09 or ClueWeb 12 is a huge task. So both is not easy, and I probably think it's, yeah, I'm not sure. I think we should maybe, I think it's still an open problem how we should handle that. I think it is too complicated for the people who provide the data set, and it is also too complicated for the people who provide the shared tasks, that they get another task to do.
Okay. Okay, thank you very much, Mike. Thank you. That was very nice.
Okay, thank you.
Presentation. We can now go on to the next presenter, Dominic. Dominic is going to talk to us about popularity bias in music recommendation. Okay.
Yes.
Okay.
Okay. Do you see the slide?
Yes, we can see you and the slides. You can start when you're ready.
Yes. Yeah, thank you very much for the introduction. So as you heard, my name is Dominic. I work at the No Center in Graz, Austria, and today I talk about the unfairness of popularity bias in music recommendation. And this is joint work with Markus from Johannes Kepler University in Linz, also in Austria, and Elisabeth from Graz University of Technology, also in Austria. I directly start with the motivation of this work. So probably all of you know that recommender systems are very useful tools in order to support users in finding relevant information in large information spaces. But they also have the issue of the so-called popularity bias. And this leads to the underrepresentation of unpopular items in the recommendation lists. And last year at Rex's conference, the group of Robin Berg has shown that this popularity bias also leads to the unfair treatment of users with less interest in popular items. And now in this work, we reproduced this study, which was conducted in the movie domain, now in the music domain. And one special property of the music domain is that there is a vast amount of items that could be recommended. And we raised the same two research questions as in the work of Berg that we reproduce. So the first one is, to what extent are users interested in popular items? So in our case, these are music artists. And the second one is, to what extent is the recommendation quality affected by this bias? And we use a data set from the Last.fm portal. It was crawled by the Johannes Kepler University in Linz. It's the LFM1B dataset, and it's quite huge. So it has 120K users, over 3 million artists, and over 1.1 billion listening events. And it also comes with a lot of metadata for these entities. So for example, it has a mainstream index score for every user. And this is a numerical value. And if it's high, then it means that the musical taste of the user is very similar to the musical taste of the mainstream. And using this score, we create 3 user groups that are equivalent to the work of Berg that we are reproducing. So we have a low mainstream index group, which are the 1,000 users with the lowest mainstream index score. We have a medium mainstream index group, which are 1,000 users with medium scores, and the high mainstream in this group, which are the 1,000 users with the highest scores. This sums up to 3,000 users with over 350K artists and 1.7 million listening events. And if we compare this to the movie lens data set used in the work of Berg, we see that we have many more items that could be recommended, because they only had 4,000 movies. And since this is the reproducibility track, we also aim for reproducibility and share this new Last.fm dataset via Zenodo. And now coming to the results for the first question. So studying the interest of users in unpopular music. For this, we need 2 definitions that we borrowed from the work of Berg. So the definition of a popular artist, which is an artist in the top 20% of artists with the highest number of listeners. And second, the artist popularity, which is the ratio of users who have listened to this artist. Then in the first plot on the right, we see the ratio of popular artists in the user profiles plotted for these 3,000 users we have. And we see that at least, or we see that around 1/3, so around 1,000 of our users are at least interested in 20% of unpopular artists. And this number also nicely corresponds to the size of our low mainstreaminess user group. And then in the second plot, we see the reason why this study is important, because here we have the average popularity of artists in the user profiles plotted over the user profile sizes. And we see that users with larger profile sizes tend to be the users who like unpopular music. So this also means that these users are the important users in the portals who create a lot of activities and traffic there. Now coming to the second question, which is the effect of popularity bias on the music recommendations. And for studying this, we use the open source framework Surprise, which is Python based. And with this framework, we formulate the recommendation task as a rating prediction problem, where we want to predict the number of listening events a user has for a specific artist. So we want to predict the preference of a user for an artist. And then we recommend the top 10 artists with the highest predicted preferences to the target user. The evaluation protocol is the same one that was used in the work of Berg. So we have a random 80-20 train test split. We have some baseline methods. We have a random recommender, most popular one, and user item average, which just predicts the average rating of the target user and target item. Then we have can-n based methods, user can-n and user can-n average, which is a hybrid mixture of user can-n and this user item average approach. And we have non-negative matrix factorization as a more complex method. And again, we aim for reproducibility and share all the Python scripts, the Python notebook, and also the recommendation implementation on GitHub. On these slides, we see the relationship between the recommendation frequency, so how often a specific item is recommended, over the item's popularity. And in the case of random, we see that it's a random relationship, which makes sense. And for most popular, we see that is very biased. So only the top 10 items are recommended to all of the 3,000 users, and all the other items get a recommendation frequency of 0. And also for the remaining 4 personalized approaches, we see a biased relationship between frequency and popularity, where it seems to be the most fairest one, so the most flat one for the matrix factorization based approach. The second thing we evaluated was the recommendation accuracy measured by the mean average error metric. And as we know, the lower the better for this metric. And in the table below, we see the results, so the accuracy results according to this error metric for the 3 user groups and the 4 personalized approaches. And we see that the low mainstreaminess group received the worst recommendations for all 4 algorithms. And this is also statistically significant. And 2 additional interesting things is that the non-negative matrix factorization based approach did not only provide the fairest results, as we saw on the last slide, but it also provided the best results according to accuracy if we compare the 4 algorithms. And if we compare the 3 user groups, we see that the best results are not provided for the high mainstreaminess group, but for the medium mainstreaminess group. And this is something we have to study further, but one reason for this could be that the medium mainstreaminess group has on average much larger profile sizes than the low mainstreaminess and the high mainstreaminess group, where the size is quite even. So to sum this up, in this work we reproduced the study of Berg on the unfairness of popularity bias in recommender systems, and they did it in the movie domain. We did it now in the music domain and verified the results. So with respect to the first research question, we have seen that there are indeed users who have interest in unpopular items, and also that these users are important because they have large profile sizes, so they create a lot of activities in the portals. And with respect to the second question, we see that these users, although they're important, they receive the worst recommendations, which is bad. And therefore, we raise a research question for the future. So we would like to find out what are the special characteristics of this low mainstreaminess user. So finding out why they get these bad recommendations. And if we know this, we can also think about ways to overcome this. So I want to thank you for your attention. We have time now for some questions, I guess, but on this slide, you also see our contact details. And as said, our data set and our source code is available on the web, and you see the links also here. Thank you.
Thank you very much, Dominic. So any questions? Okay, so one first question from Elisa. Hi, thanks for the presentation. Why did you decide to use user rating based metric instead of ranking based ones?
This had no specific reason. It was just this surprise package that we used is optimized for rating-based recommendations, so predicting the ratings. And so this was the reason that we did this. But of course, you could also use precision recall map. We also looked at that, so you get the same results.
Okay, any more questions? We still have time for some more questions if people. Okay, so I don't see any more questions. Thank you very much for your presentation, Dominic. It was very interesting. I like recommendation systems and I like music. I'm actually curious to know if I'm what's my mainstreamliness score. One of these days, I need to compute it for myself. Okay, thank you very much.
Thank you.
No questions. I'll move forward to the next presenter. So following Dominic, we have Chris and not Jimmy Lin. And Chris is going to talk about BM25. Which BM25 do you mean? That's an interesting question.
Yeah, thank you, Pavel. So I'm Chris. I am a researcher at the Radboud University in Nijmegen, the Netherlands. And this is work together with my supervisor, Arjen de Vries, and Leonid Boychov, and Jimmy Lin, who already gave two great presentations. So I'm honored that I can give this presentation. So why and how is BM25 used? So practitioners often use Lucene, let it be through Solr or Elasticsearch, and BM25 is the default scoring function in Lucene. And let me also say, for the guilty pleasure of Pavel, BM25 is still a very strong baseline, so people often use it as a comparison. It is also a good feature in learning to rank approaches, or often it's used for a first stage ranker in re-ranking systems. So you first retrieve a BM25 and then re-rank with a neural re-ranker, for example. But what did we observe? Systems that purport to implement BM25 achieve different effectiveness scores. And this can be due to many reasons. Maybe they have different pre-processing, maybe the hyperparameter settings are different, maybe they use a different IDF function, or maybe documents without at least one keyword match should be scored, or maybe there's a bug or something. Yeah, we don't know. And next to this, many slightly different variants on BM25 have been proposed in the literature. And just let me give some examples. This is work by Mulleisen et al. And here they have 4 systems that all say they implement BM25. However, the effectiveness scores are all different. The only 2 that are exactly the same are by MonetDB and VectorWise, which are both database systems, but they were both implemented by the authors of this paper. Another example is this paper. And again, there are 4 different systems and they all report different effectiveness scores for BM25. And the third example here is from the OSI-RRC workshop Jimmy spoke about before. And 7 different systems, and again, they all report different effectiveness scores for BM25. So there are a lot of differences, and where do they come from? So what we want to do for this paper is implement, say, improvements or variants of BM25 that are proposed in the literature, use a database system for quick prototyping, and make sure that the document representation is for the same for all the different variants. And we evaluate this on some newswire collections. So let me start with the BM25 as reported by Robertson et al. Let me note that there is in the original BM25 there is also a K2 and a K3 parameter, but we leave this out in this work, which is often done also in literature. And let me just present the variants. So Lucene implements this version of VM25. So there are two different, the two main differences between Lucene variant and the Robertson variant. There's a slightly different IDF function. They use 1+ in the function, and this makes sure that there are no negative IDF scores. And they use a lossy document length, and in this way they can already pre-compute a part of the BM25 function, and that way they say, yeah, it should be faster without losing too much in effectiveness. We also implemented a more accurate Lucene version where we removed this lossy document length so that we could compare these two different variants. Another variant in the literature is the one from ECIR. So here there are also two differences. There's again a different IDF function. This one may also make sure that there are no negative scores for the IDF. And there's a K1+1 in the TF part of the function. And this makes sure that the scores reported are more closely compared to the Karen-Spark-Jones weight. Another variant reported in literature is BM25L. And here there are here the authors observed that documents that are quite long are penalized too much compared to shorter documents. And because of that, they rewrote the BM25TF part a bit, and they added this delta parameter. And this makes sure that there's a correction for too long documents. And again, the IDF function is slightly different. And also here, there's the K1+1 parameter. Another variant that they proposed is BM25+. Again, the IDF function is different. And this variant is also proposed for correcting for the penalization of too long documents. It's slightly different than the previous one. This is more an extension on that work, as they observe that there are more ranking functions that have the same problem. So they generalized it, but yeah, the objective is the same. And a different and the third variant they proposed is BM25 Adapt. And here there are two main differences. I will not show the derivation for this because of time. However, the main two differences are they use a G value instead of an IDF value, which is very similar to the IDF score. However, they also correct for whether a term occurs in a short or in a long document. And they use a K1, a term-specific K1 value. And the last variant is this one. And here they model the nonlinear gain of observing multiple occurrences of a query term with a log function. So we implemented all these variants. All these variants have been implemented in different systems, so normally it's hard to compare. However, instead of implementing them in one IR system, we implemented in a database system, so we can easily compare the variants. And then the database system takes care of the data processing for you. So what are the results? As you can see from this table, the effectiveness scores are very similar. There are no significant differences between any variant on all collections. So yeah, we do not see any differences between all these variants. And in terms of efficiency, we have two parts in this table. So the upper part is the two Lucene versions implemented using Ansorini. And we see that there is the accurate variant and also the default variant are about have about the same runtime efficiency. And the lower half are the database variants. And here you can see that there is also no differences in time due to differences in the BM25 variants. So yeah, there does not seem to be a speed up regarding which variant you use. So yeah, we validated IR prototyping using databases. It's easy to compare slightly different formulas, as you only have to tweak the SQL query a bit. So it doesn't matter which BM25 to use. Well, it appears not to be. The differences in effectiveness scores are marginal. And yeah, for leucine, the document length compression does not seem to affect the effectiveness scores that much. However, there's also no improvement in efficiency. So they might as well swap to the more accurate representation. And of course, there's also a benefit in using maybe an IDF score that is not negative, but yeah, for the effectiveness scores, it does not matter a lot. So thank you.
Okay, thank you very much. Also a fast talk, so we have plenty of time for questions. As always, please use the Q&A for the questions. And by the way, I'm happy to see that I don't have to worry about which BM25 I use in my experiments. So no questions. I have to say that this was a very clear presentation, so I'm not surprised that people don't have any questions, but
well, if there are any questions, I'm of course also reachable via Slack, so I can also answer questions there if there are any.
Of course. So if there are no questions, I guess everyone wants to have lunch. So besides this being the first conference that you can attend on your pajamas, it's probably the first conference that you can cook your own lunch. So I hope everyone has enjoyed the session. Thank you very much for all the presenters. All the papers were great and the presentations were great. Thank you for all the attendance, and I hope to see you on the next sessions.
Yeah, thank you, Pavel. Let me just remind everyone, we have the lunch break, as Pavel was saying. So the next session will resume at 2 p.m. Where we will have the keynote by Jamie Callan in webinar A. Right after the keynote, we will announce the winners of all the best paper awards, best demo, test of time, etc. So make sure everyone to be there. All right. Thanks, everyone.
Goodbye.
Hi.
Hey, how are you? Let me hand over the host to you.
Okay.
All right.
Okay.
Okay, it's all yours.
Okay, I'll leave it here. I'll leave it connected, and I'll have to get your slide.
Perfect. Excellent. Thanks, Boy.
Okay.
I'll be leaving now. You have the webinar now, no? Not Rui?
Sorry, Javier.
Do you have the webinar now, right? So I can leave the meeting.
Yeah, you can leave.
Okay. Thank you very much.
Thank you. Hello, Yashar.
Hello.
I'm just setting up Philippa to help you. I will promote the speakers shortly.
Thank you.
Just a minute.
Can the speakers please raise their hands?
We have.
Nice to meet you.
Hiya.
Hello.
David Maxwell as well. He's the speaker of the first one.
Okay, David Maxwell. Yes. Okay, he's there. Ali. I think for now, all the speakers are already promoted.
All the speakers?
I mean, we're missing a few speakers, but I think they are not,
Yeah.
they didn't join yet.
Okay, so do you guys want to quickly check your slides and see if it's...
Hey, yeah, sure.
Hi. David, let's go with order. Do you want to go with your slides?
Yeah, hold on. Let me push that button and then share screen, PowerPoint. There we go. Do you see them?
Yep.
Cool. I think that's it then. And I'll stop sharing for now so others can test it, right?
Yeah.
So you shouldn't see them anymore. I'll turn off my camera.
So should I go ahead and share mine?
Yes, please.
So you guys can see this, right? I'm sorry, can you see?
Yeah, we can see slides. Now it's in full screen.
Yeah.
Do you want to go a couple of slides and see if everything's fine?
Sure. Yeah.
Okay. One question. Can you pronounce the name of the authors just so that if
my name is Wei Zhong. The other guys, Shoriel, Rohati, Jian Wu, Li Giles, Richard Zanibi.
Okay, thank you.
So I just stopped sharing from here. Oh, okay, let's see.
Ali, are you there?
I'm sorry, how can I stop?
You just, on the corner, you can mute on the bottom left corner on Zoom, you have mute and stop video.
Okay, I just stopped just now, so
you have stopped the video, but you just have to mute it as well.
Okay.
Yeah, that's it.
Ali, would you like to share your slides?
Yeah. Can you see the slide?
Yeah.
Yeah, that's it. Thank you.
Thank you. Ali, the voice quality is not good. Do you have a headphone or something that you can use?
No, unfortunately, I don't have that. I can speak loudly.
Okay, there's a lot of background noise apparently there.
Okay.
Do you hear it in your place as well, or is it just the computer?
It's from my laptop.
Oh, okay.
I can hear a really loud buzzing.
Right. Okay, that's fine.
I can present with my phone if it's okay.
Do you want to quickly test it?
Yeah.
Okay, let's just test it.
Okay, thank you.
All right. I think Fedor is also now joined.
Okay, I'll promote him.
Fedor,
Okay.
Nicola.
Okay. All right. He's promoted.
Yeah, thanks. Hi, Fedor. Do you want to? Your voice is not coming correctly. Ali, do you want to mute your mic and stop your video for now? Fedor, something is wrong with your voice. It comes very squeaky.
Sounds like a chipmunk's voice. Bye-bye.
Yeah, I don't know how we could listen to that talk, but the harder we ask questions. Okay, Ali, would you like to go and test your slide using your phone, please?
Yes.
Yeah. So the voice is much better now. If you can just
Yeah, I'm trying.
Wait, you can turn off your video and turn it on when it's your time, okay?
Okay.
On the corner, you have it. On the corner, you have a stop video.
Yeah, sure. Can you see my slide now?
Yeah, I can see it. Do you wanna go through a couple of slides, see how it works? Yeah, that's fine. Yeah, that's fine. You feel comfortable with that?
Yeah. That's okay.
Okay, that's perfect. The voice is coming very good. Okay, thank you very much.
No problem. Thank you.
Yeah, let's just. You might want to close some of the apps you have open in case.
I think you're just missing one of the speakers, right? The Kevin.
Yeah, I haven't seen him yet.
Yes.
Wei Zong, do you want to stop your video until it gets your time? Thanks.
Hey.
Hi, it's much better, yeah?
Better.
Okay, thanks. Can I try share my slides?
Sure.
Works?
Yeah, it looks okay. Thank you. Yeah,
Okay.
just mute and also stop your video until it gets your turn.
How do I do this? Stop sharing.
So we have Hossein and Kevin. If you are in the attendees, please raise your hand so we promote you.
Don't see them anywhere. Can I just start? Because we're 5 minutes in.
We can, well, I think we have 1 minute still.
Oh, right, okay, fair enough.
But I still waiting. I don't know whether the organizers start the session and then pass it on to us.
I think you can, well, 1 minute and you can go.
Okay.
Okay, and David Maxwell will go first.
Yeah.
Okay.
Okay. Hello, everyone. Thank you very much for coming to the last session of the second day of ECIR. We have a very interesting session today. It's very diverse topics are going to be covered. We have two journals, invited journals, one by David Maxwell and his colleagues, and the other one by Kevin Roitero and his colleagues, and also a bunch of interesting and diverse topics that are going to be covered such as formula retrieval, query-aware context, community prediction, test collection, and entity embedding and entity retrieval. But we start with the first talk of the session. David, I'll pass it on to you.
Thanks, Yashar. So good morning, good afternoon, good evening to you all, wherever you are in the world watching this. I appreciate you coming along, and thanks to the organizers of the conference, and also thanks to those who selected this paper to be presented, because this is obviously, as Yashar just said, an IRJ paper. So Yashar is actually one of my co-authors, and Leif is the other one. Leif being my PhD supervisor. This stuff was undertaken towards the end of my PhD. It's actually part of my PhD thesis. And as the title suggests, it's a user study on examining result diversification and how it affects people's behavior and search performance. Right, so if we consider search tasks, they're obviously quite complex in nature, and it can be quite aspectual as well, because we need to consider different facets, different dimensions, so on and so forth. So as an example, let's take a good old Trek topic, wildlife extinction. If you read the topic description, there's text explaining you need to find different species of animal, the country involved in trying to prevent the animal from becoming extinct, different measures that are taken, so on and so forth. You can split that further down. Different species of animal might discuss giraffes, rhinos, whatever you want. This is particularly useful to have searchers learning context, where you need to obtain a really broad overview of the topic to get an overall picture of what's going on. The more you learn about a topic, or the more different or diverse aspects you learn about, the better your understanding of the topic should be. One way, of course, we can do that is we can diversify the search results, as we allude to in the title of the paper, right? So again, we have our topic description here and our query in our search box, wildlife extinction. With a non-diversified system, we would expect maybe a set of results like this. Imagine this is like a ranking of the top 5, where elephants seem to be the order of the day, and we learn lots about elephants, but little about other animals that are endangered. Whereas with a diversified system, it mixes things up a bit, and perhaps we get a better understanding of the state of play with other species of animal that are endangered. So the question is, do people learn more through diversification? And of course, diversification has been examined in depth. I can think of many, many different PhD theses just off the top of my head to talk about it, and papers and so on. But I think it's fair to say a lot of these focus primarily on testing algorithms and so forth over collections. But people are generally not considered. How does it affect their behavior, so on and so forth? And we know that diversification clearly brings benefits. But is it advantageous to diversify search results all the time, for example? So the question I wanted to answer in this study was, how does diversification affect the behavior and performance of searchers? With a particular nuance to stopping behaviors, because that was the focus of my PhD thesis. So that's the reason why I chose that. So in order for me to be able to explain to you what I did in 15-ish minutes, I need to give you guys a little bit of an idea of information foraging theory, because we use that to prime our hypotheses. Okay, I'll just ignore that. So with information foraging theory, which is based upon foraging theory from examining animal behavior in the wild, trying to forage for food, we can imagine with a search session or a search page where we have a query and then a set of results here. It's typically the set of results that you examine are typically modeled as what we call a patch of information, from which we then enter and we analyze that particular patch for gain, for knowledge, right? And they say, or the theory suggests that the time taken for you to get to that patch is the so-called between patch time. So that's the time it takes for you to enter the query, to wait for the search engine to bring back your results, and for you to be able to enter the patch and start examining for content for relevance rather. And then the within patch time is the time that you spend within the patch assessing documents, judging them for usefulness, for relevance, whatever, and then eventually you'll stop. One really neat thing about theory is that it also allows us to predict the so-called optimal stopping behavior, or the optimal stopping point, the points at which you should stop examining content within a patch and move on to another patch, or stop entirely, right? And we can represent that graphically. So with this little thing here with the x-axis representing time and the y-axis representing gain, we can plot what's going on. So the between patch time could be shown as a little line here, which might be quite hard to see. I don't know, depending on your connection, where time goes on, but you're not gaining anything because you're not in the patch yet. And then once you enter the patch and you start reading things and judging things and so on and so forth, you're gaining information. So you're developing a rate of gain. You have a gain curve, right? What the theory says is if we plot a tangent from the origin through to past the curve, and the point at which the curve intersects the tangent is the so-called optimal stopping point. Why? Because your rate of gain after that is lower than your rate of gain was before. So the theory says you're probably not going to get as much value from continuing your search in this particular patch. That's important because our hypotheses are based on this particular theory. What did we do? So we need to talk about the tasks very quickly. I'm sure many of you will understand these. An ad hoc retrieval task is one thing that we asked our participants to look at. Find relevant documents to the given topic. Doesn't matter if it mentions the same thing again and again and again in different topics. As long as you're able to identify them and mark them or save them, that's okay. And then our other task was an aspectual retrieval task. So instead of just finding relevant documents, we wanted people to find documents that considered unseen aspects of the topic. So using our wildlife extension example again, a different species of animal that is being discussed, for example. So those are our two topics. And then we have some plots, again, to try and show some hypotheses here. So we have gain curves, where our gain for an ad hoc task is the number of relevant documents found. For a diversified system, a gain curve could look like that, or for a non-diversified system, apologies. And then for a diversified system that diversifies content, we might imagine a similar sort of stopping point. Gain curve for the non-diversified system might be higher because it's just going to bring back relevant content regardless of whether or not it's talking about different aspects. That's the hypothesis anyway. So under an ad hoc search task, stopping points on average should be similar over both systems. And then for an aspectual search task, we would expect rather a diversified system to have a higher gain curve or a higher rate of gain earlier on than a non-diversified system because it's returning more aspects. So you should be able to identify more aspects quicker, right? So we would expect there to be a bigger difference. The gain curve on a non-diversified system will be much shallower. Therefore, the tangent would intersect in the x-axis, or the x-coordinate would be much, much later on. So with an aspectual task, the foraging theory might suggest that you would stop later on a non-diversified system. Okay, so those are the hypotheses that I want to bring up here. A very brief overview of the methodology. We had 51 crowdsourced workers from AMT. We employed all sorts of measures. You can ask me a question on that later on. The task goal we set was to basically find at least 4 relevant documents for ad hoc tasks, and for spectral tasks, find at least 4 relevant and different, talking about something else. Simulated work task, you have to write a report. For the collection and topics that we used, it's all basically chosen to be consistent with my PhD work, to use a consistent collection instead of topics. With an older set of news articles, I appreciate that, might be an issue. And then we had our 2 systems, a non-diversified system which just employed BM25, and a diversified system which employed BM25, re-rank things according, or with XQuad. The details of which are all in the paper if you want to go read that. We had 2 different color schemes and logos to try and help people differentiate between the 2 systems. So that's what this hula and yo-yo search thing is. We just made up some names. And then the overall design of our study was just 2x2 design, taking into account the 2 different kinds of systems and the 2 different kinds of tasks, using a Latin square to rotate them. So we get our 4 combinations: non-diversified system ad hoc task, diversified system ad hoc task, and the same for our spectral. And then this was all done over our search system called New Search, where we logged all sorts of behaviors and we asked people questions at the end of each task, like how did you think the system performed, blah, blah, blah. And these are some screenshots here. So the non-diversified system had a purple bar, the diversified system had a green bar. That's pretty much the main difference, of course, except for the ranking too in the diversified system. And then for our topics, the topics that we selected, there were 5, including the one we used for our practice topic. But you can see we extracted some entities or aspects from these particular topics. So for wildlife extinction, we said, okay, different species of animal. So we had to go and manually curate ourselves, the 3 authors, the 3 of us, went through all the Trek relevant documents and we pulled out the different species of animal that were being discussed. So we had our gold standard to compare everything against, and we did that for each topic. Better to do it over an entity-based approach or entity-based aspects over the other, which leaves the door open for subjectiveness and people to agree and disagree. It's either there or it's not with an entity-based aspect. So it's easier for us to reach agreement. And then finally, our measures, the same for the ad hoc task, the sort of the standard stuff, precision at K, interactive precision. But for our spectral task, we used something called aspectual recall, which was defined in the late 90s, early 2000s Trek diversity or aspectual tracks that were going on, where we consider the fraction of documents which contain 1 or more unseen aspects. So the example here, if you have 5 new aspects in the top 5, your spectral recall at 5 is 1, 5 divided by 5. And then I mentioned this earlier, the gain that we used to measure how well the systems performed. For our ad hoc task, it was the number of Trek relevance saved, and for our spectral task, it was the number of Trek relevance saved, identifying at least 1 new aspect in the documents that have been saved. Whew. Right, now to the results very, very briefly. I realize I don't have that much time left, but summarizing 28 pages in 15-ish minutes is quite a challenge. Were the systems different? That's the first question that we wanted to sort of answer. And we needed to basically make sure that the performance of the non-diversified system, the way we'd set it up versus the diversified system, was sufficiently different that people were seeing more aspects or entities of the topics when they were issuing their queries. So just to show you a table or an extract from the paper, we have our non-diversified system on the left and our diversified system on the right. There was a difference in the number of queries that were issued, more in a non-diversified system, interestingly, but the mean P at 10 was pretty similar between the two. But then when we look at the aspectual measures, spectral recall at 10, we're getting a value of 2.1 on average. So that's roughly saying 2.1 new entities found in the top 10 ranking for each query. And then for the diversified system, pretty much nearly double that on average, at least. So looking at these results and everything gave us confidence that the 2 systems were indeed offering a broader overview of the topics that were being examined by the participants. Next question, did this reflect in the number of unique entities that people actually found? Yeah, it did. There was a significantly more entities that were found on average over, for example, looking at the aspectual tasks results, the diversified system, people were finding roughly 7, give or take, and 4 new entities over the course of a search session. Now, this was cool because it showed that people were identifying more aspects, but when we looked at the experience results from the surveys, the results pretty much contradicted what we were seeing with the empirical evidence. People were finding it really, really hard to discern between the 2 systems, and they were, as it says here, largely ambivalent to the performance of the 2 of them. So we had a Likert scale, 7 points, basically asking people to judge which system was better for which task. Most people went straight down the middle as a neutral sort of position, unable to discern the difference. And indeed, in the qualitative aspect of the questionnaires at the end, people were saying, I don't really know what the difference was. They felt like they were the same system to me. So people are saying one thing, but the evidence is suggesting something else. Looking at some behavioral measures as well. Don't worry, we're not going to go through all of this. Let's look at the aspectual side of things again. You can see here that there are slightly more queries issued on the diversified system, on average. slightly fewer documents examined per query on a diversified system. And then in terms of stopping depths, how deep people went to on average, the stopping depths were shallower on a diversified system, which meant a lower probability of likelihood of clicking on a result on the SERP, which was a significant difference. But anyway, what I want to point out is the stopping depth, right? So if we remember our little graph or our plot from earlier for the aspectual task hypotheses from IFT, it said that with an aspectual task, information foraging theory would suggest you would stop later on an undiversified system. On average, we're seeing that, right? So yeah, so 15.73 to 12.85. So that's something cool, interesting finding at least. And then the final thing I want to show you, because I'm running out of time now, is just a more direct comparison between the two hypotheses we had at the beginning versus what we actually saw. So what we did here was we took all the session data over the two systems and the two different tasks, and we could compute at different intervals of time what the gain was people were obtaining. So we can plot here the gain on the y-axis. So relevant documents for ad hoc and relevant and different documents for the aspectual tasks over the first 100 seconds of the search sessions. We just took it to 100 seconds just to see what was going on. And we could then plot every 10 seconds what the gain curves looked like. And we can see for the green lines, the diversified systems over the aspectual task on the right, for example, we can see it starts to sort of split off and get higher over time. Whereas, 1 minute, okay. And whereas with the ad hoc task, the curves sort of the plots sort of intertwine between one another. What I then do for this presentation is I plot the curve just to show you. You can look at the paper to see how we did all of that, and then plot the tangents to the curve, which basically provides some nice supporting evidence, visually at least, to show you that under an ad hoc task, stopping should be similar, more similar so than the aspectual task, which has more of a gap. So we can see that when you're using an undiversified system, you're actually having to go deeper or spend a bit longer on the aspectual task, which is a cool finding and suggests that the theory in itself is pretty sound, at least from this point, our studies data. So the takeaways, I think it's fair to say that diversification does aid searchers. People are able to find more relevant content, more different aspects, perhaps even on a task that does not demand it. But searchers are largely ambivalent to diversification and what's going on. It could be a variety of reasons, issues with my study or our study, a lack of subjects, maybe the systems weren't different enough. Maybe we needed even more of an effect to see what was going on. But again, we could see that they were working as intended. But perhaps the more likely thing, in my opinion, at least at the moment, is a lack of change of observables. So, you know, I did a study that was presented at ECIR2020, again with Leif and Yashar, on varying the length snippets. We made them longer, shorter, got people to try different systems. Which ones did you like? And people were much more likely in that study to say, I preferred the ones that were longer because I felt more confident with my decisions. But here we're doing something really, really subtle. We're only changing the rankings and we're not changing anything else in the interface with the exception of the colored bar at the top, but that doesn't really make much of a difference, I would imagine. So perhaps that's the key thing here. And it certainly matches up with other studies looking at diversification in the past. And then the final point, foraging theory has made some really credible predictions on search behavior. Just to show you, there were two hypotheses there. There's more hypotheses in the paper, so I invite you to go and have a look at that. But it's a nice demonstration of a theory-driven approach using IFT or search economic theory or the IPRP, for example. We can use them to try and drive what we think might happen in an experiment and then see whether or not that holds. And if it doesn't hold, maybe then we can adjust the theory and make it better in the future.
Thank you very much, David.
Yeah, sure.
We should we have only like 1 minute for questions now.
Sorry, I'm sorry. I was enjoying it too much.
So we have time for one question from the audience. Either raise your hand or post it in Q&A. Okay, so due to to the lack of time, we'll just go to the next presenter.
Thank you.
Thanks again. Great job, David, for presenting our work. Thank you very much.
Thank you. Cheers.
Take care. So yeah, Wei, are you ready?
Yes.
Okay, it's my pleasure now to introduce Wei Zhang. He's going to present the next paper, Accelerating Substructure Similarity Search for Formula Retrieval. Please go ahead.
Yeah, thanks, Yasha. My name's Wei Zhong. This work is from ECIR project. I'm going to present on accelerating substructure similarity search for formula retrieval. This collaborative work with Shaurya Rohati, Zheng Wu, DJS, and Richard and Yu. So, what is formula retrieval? According to our context, formula retrieval is just like full text ad hoc retrieval, except you can now enter some of your keywords as mathematical expressions or formulas. So in this work, we are going to only focus on single query with isolated formulas to start. So we use the operator tree representation to carry and capture the semantics and structural information in expressions. So operator tree is a representation that parses an expression into operators and operators while the operators are located at leaves and the operators are internal nodes. Okay. So how is
sorry to interrupt you. Can you disconnect your camera because the sound is not very good? Maybe if you disconnect the camera, it will improve.
Oh, let me try.
I'll do it for you. Okay. Can you continue?
So you can hear. Okay. Can you hear me?
Yes, it's much better.
Okay. Thanks for helping me click. Yeah. I just go over from these slides. So how is Maris similarity? Identify query and representation. More specifically, to score the similarity using a weight sum of those matched in the common values. So the weights for each node y node is and
your voice quality has not been improved.
Oh, I'm sorry for this, but I don't know.
Do you have are you presenting it via your laptop?
Yeah. Yes.
Do you want to connect with your mobile phone? We can just go to the next speaker, and you can just go after that.
For my old mobile phone, I don't think it can be better than this. So I have a cable directly connected to my laptop, so it should be better than that. So can I just try?
Or if you have a headphone, put a headphone on. Maybe there's some echo going on.
I'm sorry, I don't have any headphone around me.
Okay, just continue then.
Okay, sorry for this. So I will just move to the next slides. We further assume that if the leaf root passes in the representation match, then that indicates the corresponding structure also facilitates our calculation of maximum matching problem, which I was just showing here slides. So in real world, what we are seeing is more nodes to and match. So doing this work, is try to find the widest common subtree between expression representations and identify those leaves within that common subtree. Is what we find those leaves for measuring similarity. So intuitively, what we build is just inverted index based on that, because we kind of base everything on paths. So we use we break down the query and the document formulas into passes and index them using their expression ID as well as the subgroup notice. So that we from those passes by grouping them and IDs at the first time. The similarity score calculated our actual size. The problem with the above inverted index is if you perform a naive search on this index, you are quite expensive.
Excuse me. Wait, I think there's too much noise. We cannot follow. I'm afraid. I think it's best to stop the talk now, because it's
okay. So
it's not really easy to hear and follow your talk.
Yeah, I understand. So can you hear me now? I just want to mention one thing.
Sure.
So I have a YouTube video of my recorded version when I rehearse. So I can send you that link. Is that okay?
That would be great. If you put it on YouTube and share the link with the organizers, then they can post it on Slack channel.
Sure, sure.
Okay, thank you very much. Apologies for cutting your talk short, but due to the technical challenges, we cannot continue.
Okay, so should I send to which organizer?
I think the ECR organizer will be in touch with you.
Okay. Sorry.
No worries. If you have any questions from Wei, you can just contact him via Slack or email. Okay, so Ali, are you ready? Can you stop the video? Okay, thank you.
Yes, yeah, sure, I'm ready.
Okay, so now we're going to the next talk of the session by Ali and his colleague on a paper with the title Relevance Ranking Based on Query-Aware Context Analysis. Please start.
Yeah, sure. Can you hear me well?
Yes, please start.
Yeah. Hi, everyone. My name is Ali. I am from University of Massachusetts Amherst. I am going to talk about relevance ranking based on query-aware context analysis. And this is a joint work with Razi Rahimi and James Allen. Our work focuses on relevance ranking, which is the task is ranking document related to the query. For example, consider that we have a query with 3 words, and we want to retrieve some document and rank them based on this query. And then we have, for each document, we have a relevance judgment. And in the ideal case, we want to have all relevant documents on the top of the ranking. But there is a problem that there's a main problem in relevance ranking, which is the vocabulary mismatch. I discussed this, I explained that with an example. For example, consider that we have a query, which is the international organized crime. I show a relevance document for this query here. And as you can see, we have 2 exact match for international and 1 exact match for organized. But we don't have any exact match for crime. But there is a lot of terms in the document that are semantically related to the crime. How we can decide that which term is related to the crime? Possible solution for this task is that query expansion latent models, translation models, and embedding. And recently, there's a lot of paper on embedding-based retrieval models. But the main question here is that what is the relationship of the match to the relevance? How we can decide that which match is a signal for the relevance? So in this paper, we consider human judgment process as a trait guideline. In a trait guideline, they mention that a human decides that a document is relevant to the query or not based on 3 steps. At the first step, a human detects relevant location. And in a second step, decide about the local relevance for each location that detected in the first step. And in a final step, based on an aggregation over the local relevance, decide about the relevance, decide that this document is relevant or not. And we consider this, and we want to model the relationship between the match and relevance like the human judgment process. So we should simulate these 3 steps in our model. As a first step, we want to have a detection strategy. And we just consider an assumption, which is the query-centric assumption. Based on this assumption, relevant information only occurs in the context around the query terms in the document. For example, for international organized crime, we have 3 exact match in the document, and we can see the terms around these locations. So if we have a window for each location, then we have context of query term in document, and CQID is a context of query I in document, and 2H plus 1 is the size of the window. So now we have the location that we need in the first step. In the second step, for each context, we need to compute the relevance score. Given context and query, we should compute the local relevance for each context. So based on the constraint that we have in information retrieval, this relevance score should satisfy the constraint that we have. For example, this relevance score should satisfy exact matching, semantic matching, importance of query terms, and proximity. So we modify log logistic model that we have in information retrieval because the log logistic model satisfy all constraints that we have in information retrieval. We modify this based on the context and query that we have. So given the context and query, the score of the query and the context is the summation over all query that we have, and log of similarity between the query terms and the context plus lambda divided by lambda. The role of lambda is to consider the global importance of current query term. And with this formula, we can have distinct query term, not only by exact matching, also by semantic matching. This is an interesting point in our model. And the similarity between query term and the context can be computed by the similarity between the query and each word that we have in the context. And also we have a threshold for semantic similarity between 2 terms because we want to ignore the noise of the terms that we have in the context. The threshold here is the theta. So now we have a formula for local relevance score that can satisfy exact matching, semantic matching, importance of query terms, and proximity. But there's a problem with our model that we saw in our experiment, which we named that semantic difference. I explained that with an example from Trek Robots. Consider that we have a query that is a Hubble telescope achievement. And we already know that the similarity between Hubble and telescope is much higher than the similarity between Hubble and achievement. And we have two local contexts that the centric of the context is Hubble. And we already know that Hubble occurred in these two contexts. So if we have a term in the context related to the achievement, it has much more information for us to decide that which one of these contexts are relevant to the query. Because if we have a camera here, because we already know that the Hubble is occurred in the context, it cannot have a lot of information for us. So in this case, LC1, which is a local context one, more likely to be relevant to the query. So if we want to have this feature in our model, we add another component to the previous formula that we have, which is this similarity between the query centric and current query that we are considering. And the dissimilarity between the two queries can be computed by 2 minus cosine similarity between embedding of the words that we have. So now we are going to the next step, which we should decide about the global relevance. We have some context in the document, and we want to decide about the global relevance. There's two approaches that we consider in this paper. The first approach is disjunctive relevance decision, LCD. For this approach, we just take the maximum score that we have for a query and context in the document. And the second approach, we use an aggregation over all scores that we have for a document and a query. And final document score can be computed by integrating our score to any retrieval model as a way to look at the importance of the query in the document. And in our experiment, we used a language model, BM25, and large logistic model. So in this paper, we have three research questions to answer. The first one is that how does our model perform with different retrieval function to weight query terms? And the second one is that how good our model is in comparison with existing retrieval models. And then the third research question, we are going to show that which one of these combining relevance evidence can be good for this task. We consider three collections. The first one is the robots, which is a news collection, and WT10G and GOV2 are web collections. For the first research question, we consider three retrieval models, language models, BM25 and log logistic, and integrate our model to three retrieval models that we have. And as we can see, the other model can improve the performance of the all retrieval models in all collections. An interesting point here is that the improvement over GOV2 is much higher than the two other collections. This is because that the GOV2 is much noisier than the two other collections, and our model can ignore the noise of the terms in the document by our threshold that we consider in the model. For research question 2, we compare our model with existing retrieval models, and we consider SPM that use the proximity of the query terms in the document, LDA that use the topic of the terms in the document, and EQE1 just consider the semantic between the query terms and document. But our model can have all of these features in one model. And also the experiment can show that the performance can improve if we have all these features put together. And research question 3 is that how we can decide that between LCD and LCA. As I mentioned the previous slides, LCD just take the maximum score that we have, and LCA have an aggregation over all score that we have in the document. So in experiment, we show that LCD is much higher than better than LCA. This is because that LCD ignore the noise of the score that we have in the document, but we have a lot of noise in aggregating scores. And as I mentioned, we have a threshold in our model, which considers this similarity between the query term and term in the context. And we see that the best value for the theta is the 0.5, and this is true for all the collections. As a conclusion, we propose a new model for semantic matching based on simulating human judgment process. Our model can capture importance IR heuristics like proximity, semantic matching, exact matching, and importance of query term. And we show that our model can integrate to any retrieval model to have these features. Thank you so much. I would be happy if you have any question to answer.
Let's thank Ali for his fantastic talk. We have plenty of time for questions. Please raise your hand. Okay, we already have one hand raised. Can you please activate?
Hello.
Hi.
Hi, I have two questions about this. First of all, is you mentioned that for the mismatch for the mismatch problem, you mentioned the translation models would be a help. So, what kind of help can translation models for here? And the second one is
sorry, can you repeat the question?
Yeah, you mentioned the translation model can be a help in a mismatch problem here.
Right.
Yes, I don't know. Can you explain it? And also the other question is about have you analyzed the importance of query terms or treat it equally while you find the local relevance for each query term? Yeah.
Sorry, can you repeat the second question also?
Second question?
Yeah.
Yeah. Have you analyzed the importance of each query terms, because different query terms have different importance for this document?
Yeah. For the first question, the translation models can translate for each query terms, we have some translation, and this translation can be considered as a alternative for this query. For example, for the example that I show in my presentation for crying, we can have a translation from crying to dry. And there's some previous work that consider translation models to solve this problem. And and for second question, for each query terms, we have different importance. And I think in our model, we carefully decide that which term should be much more important compared to other. And I didn't analyze exactly the.
Okay.
Ali, I think we lost your voice. We hear you very difficult. Maybe if you mute and unmute, maybe it works or something.
Is it better now, Yasha?
Not really. We can hear you, but very not very good.
Yasha, can you hear me, Bill?
Yeah.
Okay.
Now it's good. Yeah. So if you want to answer the second question, she was asking, yeah, have you analyzed the importance of each query terms?
I said that for each query terms, we have a different importance that we consider in our model. But we didn't analyze exactly them, but I think we satisfied this constraint that we have in information retrieval.
Okay. Any other questions? I have a question. Have you investigated the effect of efficiency?
The effect of what?
The effect of your model, effect of incorporating semantics in the efficiency of your model.
You mean just effect of the semantic, right?
Yes.
Not really, because we have all the semantic and exact matching and importance of query terms together, but we didn't analyze that separately. But this is a good point. We should do that, I think.
Okay, let's thank Ali again for his fantastic talk. And anybody from the next talk is available? I think Hussein, are you, or anybody else's from the next talk available? If that's the case, please raise your hand. Okay. So I think we should go with the next talk, and if anybody of the authors will arrive, then we'll just go after. Kevin, are you ready?
Yes.
Okay. So now my pleasure to introduce Kevin Rotreo for presenting his talk, Fewer Topics, A Million Topics, or both, on topic subset in text collection. So it's a journal that he is being invited, a journal that he's now going to present. Okay.
Okay. So, well, good morning, everyone. So I will be discussing this paper. It is a joint work between me and Stefano Mizzer from Udine and Shane Mark and Fogg from RMIT University. So we are placing this work in the effectiveness evaluation using text collection. So we have a collection of documents, a set of topics, and a set of retrieval systems. And then we retrieve a set of documents within each topic by the systems, which are then pooled, and then the relevance is assessed by experts. Then with this pool of document, we compute the effectiveness metrics such as precision, average precision, etc. And we use such metrics to rank the retrieval systems. So we can represent these settings using this table. So we have in M systems in this case, and then topics in the columns. And in the cells, we have AP, which stands for average precision, which measures the effectiveness on one system on one topic. But of course, other metrics are possible. And then if we compute the we want to rank the system. So in the end, we compute, for example, the average of the AP scores over the topics. And what we get is the MAP, which stands for mean average precision, which represents indeed the mean effectiveness of each system. And we use that to rank the retrieval systems in order of effectiveness. So we asked ourselves, okay, what happens if, how many topics we should use in this setting? So we might use a set of topics or a larger set of topics. And of course, if you reduce the number of topics, that reduces also the statistical significance of the whole collection. So we want to investigate which is the trade-off between the evaluation costs and the reliability of the whole collection. Thus, in this work, we investigated the topic selection strategy and topic subsets in general. So using fewer topics, if you recall that the table that I just presented you, means using fewer columns. So we might have, in the first case, which is the upper table that you see here, 3 systems, 5 topics, and we might compute the MAP score of each system using, for example, in the first part, the whole 5 topics. And if we reduce the topic set, we basically reduce the columns. So in the second column, you see that we just selected the topic number 2 and number 5. So we end up using an MAP score using just 2 topics. And we want to investigate, okay, if we do so, which is the relationship between the first map value and the second map value? So basically, which is the effect on how the effectiveness of the systems is changed? So how the systems are ranked differently. Are we still able to guess to assess which is the most effective system and the least effective systems, or there are like some swaps in the ranking? So there is some background in this kind of work, and many works indeed discuss the reduction of topics in different ways. Basically, the first one is random sampling, and concludes in 66 to 2000, like 75 to 250 or even 1000 topics should be used. Some other work suggested that 25 is not bad. And some other studies says that, okay, the more you have, the better, like 25 is good, but 50 are better, and indeed like that. And some other work, like in 2009, 2011, and 2013, investigating experiments on topic subsets. So the very same settings as we did. So the results can be summarized in this slide, which is from Giver et others from 2009. So in here you see a plot which has the topic set size on the x-axis, which represents the number of topics considered, and in the y-axis the tau correlation, so the Kendall's tau correlation, which represents how well the map computed with the reduced set of topics correlates with the full map computed with all the topics. So the higher, the better. They investigated 3 different series, which the best, the worst, and average. So the best series is what happens if we choose the optimal subset of topic. The worst is what happens if we select the worst possible subset of topics, and the average is just simply random sampling of topics. And they showed that the best series showed that even using a topic subset, for example, with 50 topics of cardinality 6, a Kendall's tau correlation above 0.8 can be achieved, which is good. And also the curve for the average topic set, which is in the middle of this plot, show that Kendall's tau 0.8 is reached at a much higher cardinality, in this case, cardinality number 22. So there is a bit of limitation with past work. So they used almost greedy search between topic sets, and they used relatively small ground truth, so always 50 topics. Also, statistical significance between the runs were not considered in those studies. And there was almost no characterization of best or in general of topic sets. So we investigated the following research questions. What effect does a larger ground truth, which means more than 50 topics, have on correlation curves between mean average precision values? And are the results on the topic subset still valid when we consider also statistical significance between runs? And for the final research question, we wanted to characterize the best topic sets, and we investigating whether clustering of AP scores can be an effective strategy to find and characterize the best topic sets. So we start the first one, and here you present you the data and the methods. So we use forced recollection, which ranges from 50 to 100 topics and from 26 to 96 runs. So we have a variety both in topics and runs. And we employed here a different but more efficient genetic algorithm to find topic sets that allow us to cope with this bigger amount of data. And we used AP, MAP as the original work, plus we consider StatAP for MQ dataset as effectiveness metrics. So to answer the first research questions, what we found here, you see in the first part 2 plots. In the x-axis, you have before the cardinality. On the y-axis, you have the Kendall's tau between the mean average precision scores. And in the upper part, you see the full set cardinality, so the number of topics. And in the lower part, you see the topic fraction. So this is the fraction of the number of topics. We consider the fraction to normalize all the collections from 0 to 100% of the number of topics they have. And here, each series is a collection. So we saw that even fewer topics can be potentially used if the ground truth is much higher than 50 topics. And in general, the larger the ground truth, the higher the correlation curve it is. So it appears that the more topic you have at the beginning, the higher the correlation curve you can obtain considering system ranking. Also, having a larger topic set increases the possibility of finding good topic sets, thereby leading to higher correlation. We then moved to the average scores, and we saw, which is basically selecting topics randomly, and we saw that selecting a random subset of topics appear to be a better predictor on runs in the first collection, which had less topic than the other. But then when we move to the fraction, which is the bottom part, the bottom plot, these curves tell a different story. So it seems that, again, having a larger ground truth increases the possibility to find good topic sets in general. So the more topics you start with, the more chances you have to find good topic sets. And then we move to the worst topic sets. So basically the topic sets, the rank system in the opposite way or in the worst possible way. We saw that the correlation values for the worst curve are even negative, especially for the last part, which is the million query dataset. And this is true also for cardinality much larger than the 50 topics, which is the usual number of topics used in the evaluation exercise, as used also in the past work. Moreover, a set of around 50% of the million query topics, which is around 100 topics, result in a tau correlation of 0, which means that produces a ranking of systems that has no correlation with the actual ranking of system computed with the whole set of topics. And then again, we saw that the larger the ground truth at the beginning, the more extreme correlation curve you obtain. So it seems again that the more topics you have, the more chances you have even to find worse topic subset. Okay, but someone can argue that this is kind of extreme values. So we moved to investigate the best 1% and the worst 1% percentile of the topic subset. The best 1% tells that finding the best topic subset is rather difficult, but reasonably good results do exist. So hopefully they can be easily obtained in practical cases. So it can be that collections are employing all the kind of best possible topic subsets. And again, the worst 1% curve, it's much less worrying than the worst. And indeed, when trying to find the topic set for an effective test collection, low positive correlation is not that satisfying either. So even if the worst 1% is better than the total worst, it's still not satisfying. And indeed, it's possible that some test collections have been created with topics that run ranks quite differently from what something might be expected. So still, the worst 1% saying that there are topics as subsets which might be dangerous. So if you select from a larger ground truth few topics, you might end up also in practical cases with very, very bad system ranking. This is for the first part. For the second research question is that we investigate in statistical significance. Here, if you look on the kind of plot they did, we have a full topic set. So we have a full set of topics and we have a reduced set of topics. what we did, and we have here in this plot 3 systems, and the bar more or less sketches the AP ranges of score. So we have one system which has a certain range in the full topic set and another range in the reduced topic set of AP scores. We computed whether the difference between runs, so between systems, is statistically significant both in the full topic set and then if that statistical outcome is still present in the reduced topic set. So we started, and we computed for each pair of run their mean average precision score using the full and the subset of topics. Then we computed a two-tailed t-test to determine whether the difference is actually statistical or not in both the two sets. And then we explored all the 5 possible outcomes. So here, this is a summary of the results. Basically, it tells that when we use the full collection, is it possible to statistically distinguish between the runs in the majority of the cases. Moreover, results, so MEP scores, tend to be statistically significant more often when the full cardinality is higher, and this is kind of expected results. But we saw that best and worst subset led to finding runs both in agreement with the ground truth and statistically significant, more for the best topics and less for the worst topic subset than the random topic subset. So it means that if you end up with finding best topic subset, you have also runs that are more statistically significant than random topic subset. But if you end up discovering a worst topic subset, then you see also you lose the ability of distinguish statistically significant runs. So indeed, this is telling you that best topic subset are indeed good, but you should take care of also of the worst topic subsets. And then just briefly, the third research question, so all the details are in the paper. We started from idea that if we group together similar topics and we select one representative from each cluster of similar topics, then the MAP scores in the end should be similar. Thus, basically grouping together topics, we can reduce the topic subset and hopefully find also best topic subset. So our results show that actually identifying an effective approach, so we found out that clustering can effectively identify the few good topic subsets, and in general clustering of topics based on effectiveness and also dimensionality reduction is almost always better than the average series. And this is kind of a result which is stable across collections. So we saw that actually we characterize in some way the best topic subset, which was by the means of clustering. So in the end, just to conclude, the take-home message is we saw that examining subset of larger ground truth topic sets results in best subset that are more highly correlated with the ground truth than what was found in previous work. And we saw that under large cardinalities, worst topic subset are notably worse than as was shown in future work. Moreover, the ability to distinguish statistically significance between the effectiveness of two runs is impaired where when topic cardinality is lowered. So basically, we saw that the main problem is an increase of false negative, so type 2 errors, where you reduce the topic subset you start with. And finally, we saw that clustering is indeed effective in finding topic subsets that are slightly more representative than simply considering the average or random subsets. Thank you very much. So here in the last slide, I give you the reference to the whole paper, which was published in the Information Retrieval Journal. And if you have any question, I'm here to ask. So thank you very much.
Thank you very much, Kevin, for the fantastic talk. If there is any question, please raise your hand or post it on a Q&A. Okay, I have a question. Have you guys investigated the characteristics of a topic? Whether, for example, a topic is difficult or easy, and also the task, if it's like diversity tasks, which have usually the topics usually have multiple aspects and so on.
No, okay. So in this work, we didn't consider any of that. We just simply considered like extreme curves and also percentile curves, but without characterization on topic subset. We did some experiment on that, which some of that is in the paper about so when we wanted to group topics together, if you think about that, since we group topics together based on their AP scores, we indeed consider difficulty of the topic apart from effectiveness. So we did a bit of that, but we didn't consider the things, from example, like diversification and this kind of things.
Okay, thank you very much. So we have a question. So how would you operationalize this to create better test questions? From Donna Harmon.
Okay, thank you for the question. So yeah, actually it's not that easy. So for example, we saw that clustering, so finding best topic subset is difficult and is not always better than the average. So that was not kind of safe enough to go into create better test collections. What we can take from this is that once you collect, for example, if you want to create a new test collection, or you want to create a test collection by reusing another set of topics from previous collections, for example, you can run a set of experiments like we did, and you can see, even for example with a shallow pool, so we didn't investigate the effect of pool depth here, but you can run some kind of experiment to see whether the subset of topics that you are considering, maybe taking, for example, from all the collection, can help you in identifying like problematic situation which can happen. Maybe you have old systems and you have you select a subset of topics from old collection that you want to reuse, and you can test whether how those topics that you selected go well together or not, and whether they can lead to dangerous, potentially dangerous situation in the future.
Thank you. Any other question?
I think we have one from Benjamin Brown. You can unmute and talk if you want to make your question.
Yep. Benjamin, ask your question.
No, sorry, it was an error. No question. Thank you.
Okay. Okay, so let's thanks Kevin for his fantastic talk, and we have one more talk left in the session by Fedor Nikolov and Alexander Kotov, paper titled Joint Word and Entity Embedding for Entity Retrieval from Knowledge Graph. Fedor, please present.
Hi, do you hear me?
Yep.
Oh, okay. Hello, I'm Fedor Nikolaev. I'm going to present a paper of me and Alexander Kotov, Joint Word and Entity Embeddings for Entity Retrieval from Knowledge Graph. So what is a knowledge graph? Knowledge graphs are a way to represent knowledge about entities as a set of subject-predicate-object triples. And entity is either abstract or material object designated by identifier. For example, in DBpedia, Barack Obama has identifier dbpedia.org/resource/Barack Obama. Subjects in triples are always entities, and objects are either entities or literals. And entities are connected with other entities, literals or scalars, by relations or predicates, such as genre, known for, spouse, member of. Example, triple that represents knowledge that Barack Obama is married to Michelle Obama is Barack Obama, spouse, Michelle Obama. So there exists a lot of knowledge graphs. Most popular ones are publicly available DBpedia and Wikidata. Also, we have Yago, Never Ending Language Learning, OpenAI from Stanford NLP, Also, many companies, such as Facebook, Microsoft, or Google, each of them have their own private knowledge graphs, which they use in their products. And publicly available knowledge graphs, they are connected in this linked open data cloud or semantic web. So in this study, we focused on DBpedia. That's how DBpedia entity looks like. That's like kind of human readable representation for information about Barack Obama entity. And that's how it's actually stored as a set of RDF triples. In this study, we define 4 structural components of DBpedia. So we have entities such as Barack Obama, Michelle Obama. We have categories. For example, Barack Obama belongs to categories presidents of the United States or critics of Islamophobia. These are extracted from Wikipedia categories. We have literals. For example, Barack Obama has literals, which is his birth date, August 4th, 1961, and his gender, which is male. And also we have predicates. So each triple has predicates, and we also define it as a structural component. So birth date and spouse are predicates. So we focused on task of entity retrieval. Entity retrieval is basically when user is looking for some information about some entities, and he gives us some query in natural language. There exist 3 subtasks in entity retrieval. We have entity search, when user looking for some particular entity. We have list search when user is looking for some set of entities, and we have attribute search when user is looking, he wants to find some particular property of some entity. For example, he wants to know when Intel was founded or what is the elevation of Karakoram. Traditional approach to solve this task is to represent entities as multi-fielded documents and perform retrieval using structured document retrieval models, such as FSDM or PFSDM, which were designed, developed specifically for entity retrieval, or we can also use traditional BM25F model, and it also works pretty well. Limitation of this approach is that matching of queries to entities is only performed at word level, and it doesn't model some semantic information. So the problem is how to model this semantic information about entities. Recent research direction that allows us to do this is network embedding models. They usually based on application of word embedding methods to sequences, which are obtained using random walks on a given network. So in our case, network is a knowledge graph. Examples of these methods are deep walk, line, node to vec, and struct to vec. But there's problem is that we can't directly utilize network embeddings, existing network embedding methods, for entity retrieval in word-based retrieval models, because they don't model words, so we can't directly use them to model words in user queries. Alternative to using word embeddings is to use alternative to using network embeddings is to use word embeddings, but problem with word embeddings is that they don't utilize information from a knowledge graph. So to solve these issues, we propose knowledge graph, entity, and word embeddings for retrieval, or KEVR. It's a method that learns distributed representation of both words in predicates, literals, entity, and category names, as well as entities and categories in knowledge graph G in some embedding space. And the KEVR utilizes local structure of knowledge graph when it learns these embeddings. So KEVR consists of 3 steps. First, we perform random walks on a knowledge graph. So starting from each entity, we generate gamma random walks of length t. This is an example random walk with 3 entities, which tells us that Pierre Curie is married to Marie Curie, who is known for discovery of radioactivity. After this, we perform replacement. We randomly replace some of these entities, categories, and predicates with their surface forms. So surface forms, they come from entity labels or their anchors, anchor texts. So after we do this replacement, we get sequences and we train embedding model on these sequences. So elements of the sequences in this notation, they are Xi, and they belong to big C, which is different depending on which structural components of knowledge graph we use. And model predicts context elements based on target elements, like in a skipgram-like fashion. So to actually do the retrieval, first we embed user query as a weighted sum of embeddings of query words, which are model lengths. So here we have A is a constant, P of QI is inverse collection frequency for a query word. And then we simply score our entities by their cosine similarity of their entity embedding with the query embedding. So this already provides us ranking over knowledge graph entities. But this is a weak ranker, so we can use it in a re-ranking scenario. For example, we can re-rank top entities obtained with term-based matching method, such as BM25F, using interpolation coefficient B. Also, to fine-tune query embedding, we can perform entity linking on query and add embeddings of linked entities to our query embedding. And we weight these linked entities embeddings with linker entity linker annotation score. As a baseline in our experiments, we use the jointly method, which is based on which is similar to number of proposed similar models, which were proposed for tasks such as knowledge graph link prediction and triplet classification without particular focus on entity retrieval. So loss function for jointly consists of 3 components. First component is knowledge component loss, which is similar to trans E. Second component is textual component loss, which is CBAU, modeled on entity abstracts, trained on entity abstracts. And third component aligns these embeddings, entity embeddings obtained from knowledge component and word embeddings obtained from textual components by forcing embeddings from entity abstracts to be close to embedding for an entity for which this abstract is for. So first experiment that we did is we wanted to see which structural components are useful for retrieval. We found that using all of them are useful, but most useful one is categories, and which provides most improvement. And next come literals, and predicates add just a little bit of improvement. Then we compared performance of using raw cover and cover that uses entity linking. So we used 3 entity linkers, Wikipedia Spotlight, SMAF, and Nordlys. So we found that using entity linking always improves performance, and best entity linker in this case is the SMAF. So we also compared it to our jointly baseline. We found that cover outperforms jointly baseline, and jointly by itself without entity linking works pretty bad, but performance increases when we use it with entity linker, which shows that entity embeddings that it learns are more useful than word embeddings. And jointly that uses entity abstracts is slightly better than jointly that's trained on surface forms. Then we evaluated the ranking performance of Kever by ranking BM25F results with Kever that uses or not entity linking, and also ranking BM25F with word2vec. So we found that on average, Kever improves BM25F results, and it works better than ranking using word2vec. And the Kever that doesn't use entity linking works slightly better than Kever that uses, with exception of list search query set. And Kever works better than word2vec, with exception of some search, entity search query set, where queries are just simple entity search queries. And most performance improvement is obtained on Quote query set, where queries are complex question answering queries. This is an example query where we obtained a good improvement compared to BM25F term matching. So query is Wonders of the Ancient World, and BM25F only provides one highly relevant result in top 10 results, while using Kever, so that's just raw Kever without interpolation, provides 5 highly relevant results. So we can conclude that using all structural components of knowledge graph is useful for training Kever, and it results in highest retrieval accuracy on the BPD entity V2. And Kever is particularly suitable for improving ranking or results of complex entity search queries, such as question answering, list search, and keyword queries, where it can provide semantic relevance signal which is not captured by term-based retrieval models. So code for both Kever and baselines, runs, and embeddings are available at this GitHub repo. Thank you. That's it. Questions?
Thank you very much, Fedor, for the very interesting talk. We actually have a question lined up for you from Sahil Kopra. Sahil, do you want to ask the question live? We can activate your microphone, or you want me to read your question? Okay, I'm just going to go ahead and read it. So a question from Sahil Kopra. What is the intuition behind summing entity embedding and query entity embedding? So asking about the intuition behind summing the entity embedding and query entity embedding.
Is this about this slide? Like, why do we add?
Can we activate Sahil's Kopra microphone so that? Yeah. Sahil.
Yes. Yeah, this is about this slide only. So
okay.
what is the intention behind adding, summing up this the embedding from query vector and this linked entity embedding?
Okay, so intuition is that when we just add words, it basically doesn't give us all the information that we can utilize. And using entity embeddings that are contained in queries allows us to get more information basically from this query, which which is not captured by just using individual words. It was like hypothesis, and we wanted to see if it holds. And like as we see that entity linking helps, like it means that this hypothesis is true. But yeah, it wasn't obvious from the beginning that it would help.
Okay, thanks.
Yeah, thank you.
Any other question? I have a question. So you're extracting your information from a graph structure.
Right.
Have you investigated the robustness of your model when the graph changes and the edges are removed or new nodes are being added?
No, we didn't do this. Like all work was done on a static DBpedia 2015 knowledge graph. Yeah, we didn't do this. But I think since other word embedding methods, network embedding methods, I think they work with dynamic graphs. So probably our method also would work, but we didn't check it.
Okay. So if you don't have any other questions, let's thank Fedor again for his fantastic talk. Round of applause for you. Okay, so is Hussein here or any of his co-authors to present the work with the title Temporal Latent Space Modeling for Community Prediction? If you are, please raise your hand. So we'll just give Wei another chance to present his work now that we have time. Wei, would you like to bring your slide and share it with us?
Sure, thanks, Yasha. Can you hear me clearly this time?
Yeah, we're hearing you well now.
Is that okay? Just I don't share my video, but I just share my slides so that I can make sure
that's
my
absolutely
bandwidth
fine.
is okay this time.
Sure, go ahead.
Okay. So you guys see my slides okay, right? Should I start over or? Hello?
The sound is poor again. Maybe you want to play your video?
So there's a warning sign on my audio icon. I don't know why. Every time I start sharing my PDF, it pops up.
Okay, let me see if I can play your video and share my screen. Wait a second. Okay, so
Hello everyone, my name is Wei Zhong. Today I'm going to present.
okay, so do you want to stop your camera?
My warning icon disappeared again. Maybe I should try once more.
I think I have it. I have your talk now. I can just run it for you.
Okay, then yeah, I can wait until the question.
Exactly.
Yeah.
Okay. Right. Okay.
Hello everyone, my name is Wei Zhong. Today I'm going to present to you our work from the MathCR project, Accelerated Structural Retrieval. So formula retrieval in our context is just like full text ad hoc retrieval, except users now can enter some of the keywords as mathematical expressions. In this work, we're going to focus on the query with single isolated formula retrieval, with single formula to start. We use operator tree representation to carry and capture the semantics of mathematical expressions, their structural information in particular. The operator tree representation explicitly parses an expression into operators and operands, where operators are lived into the internal nodes, leaving operands at the leaves. We measure the similarity in our previous work by first identifying a number of common subtrees between the query and candidate operator tree representation. And then we will score the similarity using a weighted sum of all the matched nodes within those common subtrees. The weight to the matched node depends on what type of the node it is and to which common subtree it belongs. We further assume that the leaf root path match will imply the corresponding substructure are identical. This is an assumption that we try to accelerate our matching process, but also it facilitates our calculation of the maximum matching problem, as we will show in a few slides. However, in real-world scenario, you often end up saying tens, if not hundreds of nodes gets matched. If you want to count all of the nodes, that can be also expensive. So in this work, what we are trying to accelerate is we only consider the widest common subtree being matched between the two, and use the number of leaves to measure the similarity. As in this figure, this number of leaves we want to count is underscored by the red ink here. So we proposed a path-based inverted index intuitively because the query formulas and the document expressions are all decomposed into leaf root passes as their prefix from their operator tree representations. We will index the expression ID of the document expressions and also with their root and node IDs so that we can recover their structure from those linear passes by grouping their root and node IDs indexed in those inverted index. We can then calculate the similarity score based on that, as I will show shortly. However, if you perform a naive exhaustive search on the previously mentioned inverted index, you will find it can be quite expensive. According to our survey on a recent MathIR task, most of the time, our queries in our setting would consist of more than 20 or 25 terms, which is unusual in text search. And according to the right figure, most of the time, only a small number of passes will get matched and contribute to the score. So this indicates a huge potential to improve in terms of efficiency. We looked into dynamic pruning techniques successful in accelerating inverted index-based retrieval. Dynamic pruning works by estimating a score upper bound for a heat. If this heat upper bound is less or equal to a threshold value theta, which is dynamically and always equal to the minimum score of the top k candidates, then this heat can be skipped. So in particular, of the max score dynamic pruning algorithm, a set of post lists whose upper bound summation is less or equal to the threshold is also being identified. And this set of post lists is called the non-requirement set. All the post list iterators within this set can be added directly to the next candidate without looking into any document in between. And the complement set is called the requirement set, according to the literature, or sometimes required set. We have modeled our tree matching problem into a path matching problem according to our assumption. If you look at this bipartite graph described on the right-hand side, which tries to capture the path matching problems. The key observation here is if we group the passes in the two sets by their types, then we will end up having many partitions of the same, within each partition of the same type of path. And for each partition, it is a complete bipartite graph. Thus, the maximum matching between the two sides is trivial to compute. You can just take the minimal value of the size between the two to get the maximum matching in one partition. To get the maximum matching between two sub-expressions, as the example here, if we want to calculate the sub-expression maximum matching between M and N, kind of partition do they have between the passes? Since only two types of passes are attached to node M, namely var times add and var add, we can just match the passes and get the maximum matching value by summing those partition match values as highlighted in red and blue here. We can simplify, we can write down our simplified similarity measurements used more formally. So our measurement is nothing other than counting the number of leaves matched in the widest common subtree. If we name this measurement as W star, it is just the maximum value of all pairs of maximum matchings between query tree and the document tree nodes. Let WMT equals to the number of query passes rooted at M of token T or type T. Then WMT can be viewed as a partial upper bound in our case. And since this inequality does not depend on the document side, WMT can be pre-computed. We propose three strategies to assign the non-requirement set according to WMT value. The max-reef strategy explicitly assigns each posting list an upper bound, max-reef value, which equals to the maximum value of all WMT value referring to this post list T. The other strategies, instead of assigning upper bound for the post list, directly optimize a binary programming problem. Well, they try to solve a variable or binary variable X, which represents the assignment of non-requirement sets. The difference is GBP number tries to maximize the number of posting lists, while GBP len tries to maximize the total length of the posting list, both in non-requirement set. Since this too involves solving binary programming problem, which is NP hard of the sub-problems to get a feasible solution. Let's look into our indices and the substructure in more detail. We said that, well, the expressions in the document will have their expression IDs and the subroot node IDs along with the number of passes associated to each nodes and type index in our inverted list. So given an example here, well, we try to index the structure of a sub-expression rooted at D4 in the document. what we are going to do is find the partitions of this subexpression to be indexed, since only two types of passes are attached to this node D4, namely var times add and var add. We're going to write the information and append to the corresponding posting list. Information we want to store as the corresponding posting list is just the root ID of that subexpression / the number of passes associated to the corresponding type of that posting list. At some point, you need to match between a query node and a document node. In this example, since we can trace back from all the relevant posting list to get a relevant query nodes that are going to match this subexpression in the document. We can get, in this example, only query node 1 is relevant to matching this subexpression. So the maximum matching between query node Q1 and the document node D4 is what we need to calculate. And the value is, again, the summation of minimal values as we described earlier. And in our scenario, what is unique is that we can drop some of the posting list iterators during our merging process. If all the query nodes having upper bounds less or equal to the current thresholds. This is because our schema considers only the widest common subtree, while the other pruning strategies of the text retrieval need to meet every candidate posting list accumulated for the score of TF-IDF. Our final score adds additional layer, we mentioned the W star value, which we also call structural score. The final score further captures symbol similarity and penalizes over large formulas. Because of this additional layer, we need to relax our upper bound further using this U function whenever we compare the score to the threshold. We perform evaluation on two datasets. One is NTCR12, which is a known mass IR dataset. The other is MSE dataset we created from the Stack Exchange mathematics website. With much more documents in the hope that we can illustrate the full impact of our pruning algorithm. We use bpref to compare for effectiveness. They are evaluated by the query runtimes distributions out of 5 independent rounds. The first figure summarizes our pruning strategy performance. We report the runtimes for different pruning strategies using different K values and against the two datasets. MSE dataset is omitted here for space. As you can see, most consistently, the GBP lane outperforms the others. In average run, GBP can perform all other strategies, GBP lane. So this is expected because GBP strategy have tighter upper bound than max reef strategy, and the GBP lane in particular models the pruning possibility better. If we compare to existing effective mass IR system, we will have the same conclusion reflected. We outperform them in both median and max value, so we have a clear win in terms of efficiency. In terms of effectiveness, we still compare the same set of systems. We are doing single tree matching, and the best system here are using the same model, but comparing between representation and find the multiple tree matching. However, we still obtain very effective full relevance results and being rank C. Our overall result is good by wildcards query because the way we handle wildcards is quite simple. So to conclude, we propose 3 dynamic pruning strategies for our mass retrieval method. We associate structural representation to our dynamic pruning strategies, and we have made highly effective substructure retrieval much more efficient.
Okay.
It's aborted very abruptly because I have a limit of 15 minutes to say if I upload the video, since I'm not verified user.
That's okay. Thanks for sharing the YouTube link and for your very interesting work. Do we have any questions from the audience? So I have a question. What is a good platform application for your model?
So I can think of 2 applications so far. So for example, in education, students can build a database, or also teachers for their questions and the exam questions. So it helps students who forget the answers to retrieve the similar question again if they forget which page it belongs to. And also, in terms of the math stack change, it's a very popular mathematic Q&A website where a lot of people go there and ask math questions, and the top users there and the moderators here actually find this very useful to have such a system, I believe.
Thank you very much. Any question? Okay, so let's just thank all the presenters and the participants for it was a fantastic series of talks. Very much enjoyed it. So the organizer would like to take a picture of all the speakers. So if you can turn on your camera, Fedor, if you can turn on your camera so they can take a picture, that would be great. Okay, another round of applause to all the presenters and to all the participants. That concludes the session. I'm looking forward to seeing you all tomorrow for the last day of conference. Thank you very much.
Before everybody go, we just like to remind you that today we have the social events. So we'll be really happy if you all join us. We've prepared different rooms, a lot of different playlists. So please do join. Thank you.
Thank you.
Ok. Flávio, vou desligar esta sala.